Hello there, and welcome to Science for Sleep, where curiosity slows down, thoughts soften, and science is allowed to unfold at a comfortable pace. Wherever you are right now, whether you're settling into bed, resting on a couch, or simply letting the day loosen its grip, you're very welcome here. Tonight, we're going to take a calm, unhurried look at something that sounds simple at first, but quickly becomes surprisingly difficult to picture once physics gets involved. We're going to explore how big Alpha Centauri really is. Not big in the dramatic science fiction sense, and not big in the way headlines like to exaggerate, but big in the precise, quietly stubborn way physics defines size, distance, mass, and space itself. Because when astronomers talk about size, they're rarely talking about just one thing. They're talking about how much mass is involved, how far objects are separated, how gravity binds systems together, and how energy moves through empty space. And Alpha Centauri, despite being our nearest stellar neighbour, manages to stretch every one of those ideas in ways that resist intuition. Before we go any further, it's worth taking a moment to notice where you are. Maybe the room is dim, maybe the lights are already off, maybe there's a faint sound in the background, a fan, distant traffic, or the quiet hum of electronics. Where are you listening from tonight? And more gently, what part of the day or night are you moving through right now? It's interesting to think that while you're here, grounded in a single place, the topic we're exploring exists far beyond anything your senses can reach directly, separated from you by distances that don't behave the way everyday distances do. If you find this kind of slow, careful exploration calming, or if it helps you unwind as the day fades, you might consider liking the video or subscribing. It helps this small, quiet corner of science reach others who are also looking for a peaceful way to think about the universe. There's no rush though. Nothing here requires urgency. Physics, after all, is very patient. Now, Alpha Centauri is often introduced as the closest star to our Sun, which is true in a general sense, but that phrasing already hides a lot of complexity. First, Alpha Centauri is not a single star. It's a star system, bound together by gravity, made up of multiple stars moving through space in an intricate orbital arrangement. And second, closest in astronomy still means unimaginably far away by human standards. So before we even attempt to answer how big Alpha Centauri is, we need to slow down and clarify what we mean by size in a physical sense. In physics, size can refer to several related but distinct quantities. There is physical size, meaning the actual radius and volume of an object, how much space its matter occupies. There is mass, which tells us how much matter is present and how strongly it interacts gravitationally with other objects. There is distance, which describes separation through space, not just between us and Alpha Centauri, but between the stars within the system itself. And there is scale, a more subtle idea that describes how these quantities compare to familiar reference points like our Sun, our solar system, or even the orbit of Earth. Alpha Centauri challenges us because it combines all of these at once. It's a nearby system that still lies far outside the reach of direct travel. It's made of stars similar to our Sun, but arranged in a way our solar system is not. And it exists within a region of space that feels empty, yet is governed by precise gravitational relationships that physics describes with quiet confidence. At the heart of the Alpha Centauri system are two stars known as Alpha Centauri A and Alpha Centauri B. These two stars form what physicists call a binary system. They orbit a common centre of mass, a point in space determined by their relative masses, rather than one star orbiting the other in a simple way. This already tells us something important about scale. The distance between these two stars is not small. Over the course of their orbit, their separation varies significantly, sometimes bringing them closer together than the distance between the Sun and Pluto, and at other times pushing them much farther apart. From a physics perspective, that separation matters more than their visual appearance. When we look at Alpha Centauri through a telescope, especially from Earth, the stars appear close together, sometimes even overlapping as points of light. But that closeness is an illusion created by distance. In reality, the space between them is vast, filled with extremely low-density interstellar material, mostly hydrogen atoms spaced far apart. The gravitational connection between the stars spans millions of kilometers, yet the region between them is emptier than any vacuum we could produce on Earth. Orbiting much farther away is Proxima Centauri, a smaller, cooler star that is gravitationally associated with the main pair, though its orbit is so wide and slow that its relationship to the system is still studied and debated. From a physical standpoint, including Proxima dramatically increases the size of the Alpha Centauri system, not because Proxima itself is large, but because of how far it travels from the central pair during its orbit. The system's gravitational footprint extends across an enormous region of space, far larger than the physical size of the stars themselves. Already we can see that asking how big Alpha Centauri is depends on what boundary we're interested in. Are we talking about the radius of the stars measured in kilometers? Are we talking about the distances between them measured in astronomical units? Or are we talking about the full gravitational reach of the system, which extends even farther into interstellar space? Physics allows all of these definitions, but it doesn't collapse them into a single simple number. Then there's the distance from us. Alpha Centauri is about 437 light-years away from Earth. That number is often quoted but rarely unpacked. A light-year is not a unit of time. It's a unit of distance defined by how far light travels in 1 year through a vacuum. Light moves at approximately 290 kilometers per second. Over the course of a year, that adds up to roughly 9.46 trillion kilometers. Multiply that by 4.37. And you get a distance so large that writing it out in full stops being helpful. In physics, distances of this scale are not meant to be imagined directly. They're meant to be handled mathematically. The equations work cleanly even when the numbers are enormous. Our intuition, however, struggles. If Alpha Centauri were scaled down so that the Earth-Sun distance fit inside a small room, Alpha Centauri would still be hundreds of kilometers away. And yet, in cosmic terms, it's practically next door. There are regions of the galaxy where stars are separated by far greater distances. This contrast between human scale and physical scale is one of the reasons Alpha Centauri is such a useful system to think about. It sits right at the edge of what we can reasonably talk about, without losing all connection to everyday experience. It's distant enough to stretch the mind, but close enough to be measured with precision. Astronomers have determined its distance using parallax, a geometric method based on observing slight shifts in a star's position as Earth orbits the Sun. This is pure physics and geometry, no speculation involved, just careful measurement and repetition. And yet, despite all this measurement, the word big remains slippery. The stars themselves are not unusually large. Alpha Centauri A is slightly more massive and slightly larger than the Sun. Alpha Centauri B is slightly smaller and less massive. Proxima Centauri is much smaller, a red dwarf with a fraction of the Sun's mass and luminosity. If you were to line them up by physical size alone, none of them would stand out as extreme. They are ordinary stars by stellar standards. What makes Alpha Centauri feel big is not the stars themselves, but the space they command. The orbital distances, the gravitational relationships, the volume of space within which their mutual influence dominates. In physics, systems are often defined not by the objects alone, but by the forces connecting them. Gravity does not stop abruptly at a visible edge. It fades gradually, extending outward indefinitely, growing weaker with distance but never fully vanishing. So when we ask how big Alpha Centauri really is, we're also asking how far its gravity matters, how wide its orbits stretch, and how much space must be considered part of the system for physical descriptions to make sense. These are not philosophical questions. They're practical ones in astrophysics, especially when studying how stars form, how systems remain stable over billions of years, and how planets, if present, might move within such environments. For now, it's enough to hold one idea gently in mind. Alpha Centauri is not big in a single way. It is big in layers, big in distance from us, big in the space between its stars, big in the region of gravity it occupies, and at the same time made of stars that are familiar in size and behaviour, following the same physical laws that govern our own sun. As that thought settles, we can begin to shift our attention more carefully toward what physics really means when it talks about size, and why everyday language so often fails us when the universe refuses to stay small. When we ask what it means for something to be big in physics, we're stepping into a question that sounds simple, but quickly resists any single answer. In everyday life, size feels straightforward. A car is bigger than a bicycle. A house is bigger than a room. We compare objects by how much space they visibly occupy, and our intuition works well because everything we deal with exists within a narrow range of scales. Physics, however, does not have that luxury. It deals with things that range from subatomic particles smaller than anything we can see, to structures so vast that even light takes years to cross them. In that context, big becomes a layered concept, one that depends entirely on what property you're measuring and what you're comparing it to. One of the most important distinctions physics makes is between size and distance. These words are often blended together in casual conversation, but they describe very different things. Size refers to the physical extent of an object itself. It's about radius, diameter, surface area, and volume. Distance, on the other hand, refers to separation. It tells us how far apart two objects are in space, regardless of how large or small those objects may be. A small object can be very far away. A very large object can be relatively close. In astronomy, confusing these two ideas is one of the quickest ways to lose your sense of scale. Take the Moon as an example. The Moon is about 3,474 kilometers in diameter. That makes it large by human standards, but small compared to planets like Earth. Yet the Moon appears roughly the same size in the sky as the Sun. This isn't because the Moon is large, but because it's close. The Sun is vastly bigger than the Moon, with a diameter about 400 times larger, but it's also about 400 times farther away. The apparent size we perceive is a balance between physical size and distance. Physics separates these cleanly, even when our senses blur them together. When we talk about Alpha Centauri, this distinction becomes unavoidable. The stars in the Alpha Centauri system are physically similar in size to our Sun. None of them are supergiants or exotic extremes. Yet Alpha Centauri feels enormous to us because of its distance, and because of the space involved in the system itself. The bigness comes not from the stars swelling to impossible proportions, but from the scale at which they are separated from one another and from us. Another layer of meaning comes from mass. In physics, mass is often more important than size. Mass tells us how much matter an object contains, and how strongly it interacts gravitationally with other objects. Two objects can have similar sizes but very different masses. A balloon and a bowling ball might be comparable in volume, but their masses and gravitational effects are wildly different. In space, mass determines orbits, stability, and long-term evolution. When physicists assess how big a system is in a functional sense, they often mean how much mass it has and how that mass shapes the surrounding space. This is especially important when dealing with star systems. A star's mass determines how hot its core becomes, how fast it burns fuel, how long it lives, and what kind of remnant it leaves behind. In the case of Alpha Centauri, the total mass of the system matters more than the individual radii of its stars when it comes to understanding orbital dynamics. The gravitational dance between Alpha Centauri A and B is governed by their combined mass and how that mass is distributed, not simply by how large they look in a diagram. Scale adds yet another dimension. Scale is not a single measurement. It's a relationship. It tells us how one size compares to another, how one distance fits within a larger framework. In physics, scale is often what determines which laws dominate a situation. At very small scales, quantum mechanics becomes important. At human scales, classical mechanics works well. At astronomical scales, gravity and relativity start to shape behaviour in noticeable ways. Something can be big on one scale and small on another without contradiction. For example, Earth is enormous compared to a human, but insignificant compared to the Sun. The Sun, in turn, is massive compared to Earth, but modest compared to many stars in the galaxy. And the Milky Way galaxy itself, containing hundreds of billions of stars, is just one among trillions of galaxies in the observable universe. Each step outward changes what big means, not because the word is vague, but because context shifts. Physics handles this by choosing reference points carefully. Astronomers rarely describe distances in kilometres when dealing with stars, not because kilometres are wrong, but because they become unwieldy. Instead, they use astronomical units, light years, or parsecs. An astronomical unit is the average distance between Earth and the Sun. It's useful for describing planetary systems. A light year is useful for describing distances between stars. A parsec, defined through geometry and parallax, becomes useful for mapping larger regions of space. Each unit reflects a change in scale, not a change in reality. This scaling also applies to size. Stars are often described in terms of solar radii and solar masses. Saying a star is 2 solar masses instantly places it in context. It tells physicists how it compares to our Sun without needing absolute numbers. In this sense, big becomes shorthand for big relative to something familiar. Alpha Centauri. A being slightly larger than the Sun is meaningful because the Sun is our anchor point. Without that comparison, the number alone would float without intuition. Another way physics interprets bigness is through influence. How far does an object's presence matter? Gravity does not have a cutoff. It weakens with distance following an inverse square law, but it never truly disappears. This means that every object in the universe technically influences every other object, however faintly. In practice, physicists define regions where one object's influence dominates over others. These regions help determine what belongs to a system. In planetary science, this idea appears as a Hill sphere. A planet's Hill sphere defines the region where its gravity dominates over the Sun's gravity for orbiting satellites. For star systems, similar concepts apply. The gravitational reach of Alpha Centauri extends far beyond the stars themselves. The space in which planets could stably orbit, the region where comets might be loosely bound, and the volume of space that responds primarily to the system's combined mass all contribute to how big the system is in a physical sense. This is why size in physics is often inseparable from dynamics. A static picture of an object's dimensions rarely tells the full story. What matters is how things move, how forces act, and how structures remain stable over time. Alpha Centauri stars orbit each other over periods of decades and centuries. Their separation changes, their velocities shift, and their gravitational balance holds steady across timescales far longer than human history. That persistence is a form of size too, not spatial, but temporal. Time itself plays a role in how scale is understood. Large systems often evolve slowly. Small systems tend to change quickly. A molecule vibrates billions of times per second. A planet takes days to rotate and years to orbit. A star system may take centuries for a single orbital cycle. A galaxy can take hundreds of millions of years to complete a rotation. When physicists say something is big, they often mean it operates on long timescales as well as large distances. This connection between size and time becomes especially relevant when we talk about distance measured in light years. A light year bakes time directly into distance. It reminds us that seeing something far away also means seeing it in the past. Alpha Centauri appears to us as it was over 4 years ago. The light reaching our eyes left the stars before recent events on Earth unfolded. This doesn't change the size of the system, but it changes how we interact with it. Big distances separate not just space, but moments. Human intuition struggles here because our brains evolved to navigate meters, not trillions of kilometers. Physics compensates by leaning on mathematics and consistent definitions. Once size, distance, mass, and scale are clearly defined, the equations behave predictably. Orbits can be calculated, energies can be compared, systems can be classified. The universe becomes manageable on paper, even if it remains overwhelming in imagination. It's also worth noting that big is not a value judgment in physics. Bigger does not mean more important. Small particles govern chemistry and biology. Large structures shape cosmic evolution. Alpha Centauri is physically modest compared to giant stars or dense clusters, yet it is profoundly important because of its proximity. Its closeness allows measurements with exceptional precision. It serves as a laboratory for understanding stellar physics, planetary formation, and gravitational dynamics in a system not unlike our own. In physics, size is a collection of relationships. It's how matter fills space, how objects separate, how forces extend, and how systems persist. Alpha Centauri will continue to feel both familiar and immense, because it sits at the intersection of these ideas, close enough to study carefully, large enough to stretch our sense of proportion, and structured in a way that quietly demonstrates how physics handles scale without ever needing to simplify it away. When Alpha Centauri is mentioned in conversation, it is often spoken about as if it were a single object, a lone star shining quietly in the southern sky. That shorthand is understandable. Our language tends to compress complexity, especially when dealing with astronomical distances. But from a physics perspective, Alpha Centauri is not a single star at all. It is a physical system, a gravitationally bound arrangement of multiple stars, each with its own mass, motion, and role within a shared structure. Understanding how big Alpha Centauri really is requires letting go of the idea of a solitary point of light and replacing it with the idea of an interacting system evolving over time. In physics, a system is defined not just by the objects it contains, but by the interactions between those objects. A single star, isolated in space, would still be governed by internal physics, nuclear fusion, pressure balance, and radiation. But once multiple stars are bound together by gravity, the situation changes. The behaviour of each star can no longer be described independently. Their motions, positions, and long-term stability are all connected. Alpha Centauri is one of the closest and most accessible examples of such a system, which makes it especially valuable for understanding how stellar systems behave in general. At the core of Alpha Centauri are two stars commonly referred to as Alpha Centauri A and Alpha Centauri B. These two stars form what is known in physics as a binary system. A binary system is not simply one object orbiting another in a neat circular path. Instead, both objects orbit a shared centre of mass. This centre of mass, sometimes called the barycenter, is the point around which the system balances. Its location depends on the masses of the two stars. If the stars had equal mass, the barycenter would lie exactly halfway between them. In Alpha Centauri, the stars have similar but not identical masses, so the barycenter lies closer to the more massive of the two, but still outside the physical surface of either star. This detail matters because it immediately expands our notion of size. The system is not defined by the radius of one star or the other. It is defined by the space within which their mutual gravitational influence dominates, and within which their orbital motion unfolds. The distance between Alpha Centauri A and B varies significantly over time. Their orbit is elliptical rather than circular, meaning that sometimes they are relatively close together, and sometimes they are much farther apart. At their closest approach, the stars are separated by a distance comparable to the outer regions of our solar system. At their farthest, the separation becomes several times larger. From a physical standpoint, that changing separation is central to the size of the system. The The stars are not fixed points. They move continuously, tracing paths determined by gravity and inertia. Their orbital period is about 80 years, meaning it takes roughly that long for them to complete one full cycle around their shared centre of mass. This slow, deliberate motion reflects the scale involved. Large systems move slowly. The greater the distances and masses involved, the longer the timescales over which noticeable changes occur. Beyond this central binary lies Proxima Centauri, a third star that is gravitationally associated with the system. Proxima Centauri is much smaller and less massive than Alpha Centauri A or B. It is a red dwarf, cooler and dimmer than the Sun, and it emits only a tiny fraction of the energy that the larger stars produce. Despite its small physical size, Proxima plays an outsized role in discussions of Alpha Centauri, because it is the closest star to our own Sun. Its proximity has made it a prime target for studies of stellar behaviour, planetary systems, and the possibility of habitable worlds. From the perspective of system size, Proxima Centauri dramatically extends the boundaries of Alpha Centauri. Its orbit around the central binary is extremely wide and slow. Estimates suggest that Proxima may take hundreds of thousands of years to complete a single orbit. The distance between Proxima and the central pair is so large that it challenges simple definitions of what it means to be part of the same system. And yet, from a gravitational standpoint, Proxima appears to be weakly bound to Alpha Centauri A and B. Over long timescales, their mutual gravitational attraction is enough to keep them associated. This introduces an important concept in physics. Systems do not always have sharp edges. Unlike solid objects which have clear boundaries, gravitational systems fade gradually into their surroundings. The influence of gravity weakens with distance, but it does not stop abruptly. As a result, defining where a system ends often depends on practical considerations rather than absolute cutoffs. For Alpha Centauri, the inclusion of Proxima means that the system spans a region of space far larger than one might expect from the brightness or apparent closeness of the stars alone. Another key aspect of viewing Alpha Centauri as a system is recognizing that its components formed together. Stars in binary and multiple systems typically arise from the same collapsing cloud of gas and dust. As that cloud contracts under gravity, it can fragment, forming multiple dense regions that ignite nuclear fusion around the same time. The result is a group of stars born with related compositions and initial conditions, bound together from the start. This shared origin is part of what makes Alpha Centauri a coherent physical system, rather than a chance alignment of unrelated stars. From a physics standpoint, shared origin matters because it influences mass ratios, orbital parameters, and long-term stability. The masses of Alpha Centauri A and B are close enough to produce a stable binary over billions of years. Their orbit has persisted since their formation, resisting disruption from passing stars and the general tidal forces of the galaxy. Proxima's wide orbit makes it more vulnerable to external influences, but its continued association suggests that the system as a whole has remained intact for a very long time. When we think about size in this context, we must also consider energy. The gravitational binding energy of the system is a measure of how tightly its components are held together. A system with high binding energy requires a significant external disturbance to pull it apart. Alpha Centauri's central binary has a relatively high binding energy due to the masses of the stars and their separation. Proxima's binding energy to the system is much lower, reflecting its wide orbit. This difference reinforces the idea that Alpha Centauri is not uniform in structure. It has a dense, tightly bound core and a much looser outer component. This layered structure is common in astrophysics. Many systems have inner regions that are strongly bound and outer regions that are more diffuse. Our own solar system exhibits something similar, with tightly bound inner planets and distant objects in the Kuiper belt and Oort cloud that are only weakly held by the Sun's gravity. In this sense, Alpha Centauri is not exotic. It follows the same physical principles, just applied at a different scale and with stars instead of planets. Another reason it's important to treat Alpha Centauri as a system is that its internal dynamics affect everything that might exist within it. If planets orbit Alpha Centauri A or B, their stability depends on the gravitational influence of the other star. There are regions where planetary orbits can remain stable for billions of years, and regions where they would be disrupted. Physicists model these regions using equations that describe three-body and multi-body interactions, a notoriously complex area of classical mechanics. The presence of multiple stars turns a simple two-body problem into something far richer and more challenging. This complexity again feeds into the idea of size. The system's size is not just the maximum distance between stars, it is also the volume of space within which stable orbits are possible. It is the region where gravity dominates over the background gravitational field of the galaxy. It is the domain in which the motions of objects are primarily shaped by the Alpha Centauri stars rather than by more distant influences. Considering Alpha Centauri as a system also forces us to think in terms of reference frames. In physics, motion is always measured relative to something else. The stars in Alpha Centauri are not stationary. They move relative to each other, relative to the Sun, and relative to the galaxy as a whole. The entire system is orbiting the centre of the Milky Way, carried along by galactic rotation. Within that larger motion, the stars trace their own paths around their shared centre of mass. This nested motion adds another layer to the idea of size. Alpha Centauri occupies a certain region of space at any given moment, but that region itself is moving. Over millions of years, the system will drift relative to nearby stars. In the distant past, it was farther away from the Sun. In the distant future, it will be farther again. The size of the system does not change dramatically, but its position within the galaxy does. Physics treats these motions consistently, but our intuition tends to imagine star systems as fixed landmarks. There is also a temporal dimension to size when systems are involved. The stability of Alpha Centauri over billions of years suggests that its physical configuration falls within a stable range. Small systems with unfavourable mass ratios or orbital parameters can become unstable, ejecting members or collapsing into mergers. Alpha Centauri has avoided those outcomes. Its size, mass distribution, and orbital geometry have allowed it to persist. In physics, longevity is often an indicator of a well-balanced system. All of this brings us back to the original question of how big Alpha Centauri really is. When viewed as a single star, the answer would be underwhelming. It would be roughly the size of the Sun. When viewed as a system, the answer expands. It includes the distance between stars, the reach of gravity, the space available for planets, and the timescales over which these relationships endure. The system becomes big not because its components are extreme, but because their interactions unfold across large distances and long periods. When physicists talk about how heavy something is in space, they're almost never talking about weight in the everyday sense. Weight depends on gravity, on where you're standing, and on what is pulling you downward. In space, where objects are in free fall and gravity acts differently depending on distance, weight becomes a confusing and often meaningless concept. Mass, however, is universal. Mass does not change whether an object is on Earth, drifting between stars, or orbiting the centre of a galaxy. It is one of the most fundamental quantities in physics, and when it comes to stars, mass is often the single most important number we can know. Mass determines how a star is born, how it lives, and how it eventually dies. It sets the pressure and temperature in the core, which controls the rate of nuclear fusion. It governs how bright the star becomes, how long it shines, and what kind of remnant it leaves behind when its fuel runs out. In systems like Alpha Centauri, mass also dictates how stars move around one another, how tightly they are bound, and how stable the system remains over billions of years. If we want to understand how big Alpha Centauri really is in a physical sense, we need to understand how massive it is, not just as individual stars but as a combined system. Astronomers measure stellar mass indirectly. Stars cannot be placed on scales, and their interiors are hidden from direct observation. Instead, mass is inferred through motion. Gravity provides the key. When objects orbit each other, their speeds and distances encode information about their masses. This relationship is described by Newton's law of gravitation, and refined through centuries of observation. In binary systems like Alpha Centauri A and B, the orbital motion of the stars around their shared centre of mass allows physicists to calculate their masses with remarkable accuracy. Alpha Centauri A is slightly more massive than our Sun. Its mass is about 1.1 times the mass of the Sun. Alpha Centauri B is somewhat smaller, with a mass around 0.9 times that of the Sun. These numbers might not sound dramatic, but in stellar physics, even small differences in mass lead to noticeable differences in behaviour. A star with 10% more mass than the Sun will burn its fuel faster, shine more brightly, and evolve more quickly. A star with 10% less mass will burn more slowly and live longer. When combined, Alpha Centauri A and B have a total mass of roughly 2 solar masses. This combined mass is what governs the motion of the central binary system. The barycenter around which they orbit lies in the space between them, closer to Alpha Centauri A because it is slightly heavier. The stars trace elliptical paths around this point, their velocities constantly adjusting as their separation changes. The fact that we can observe this motion over time is what allows astronomers to measure their masses so precisely. Proxima Centauri adds another layer to the picture. Proxima is a red dwarf star with a mass of only about 0.12 times that of the Sun. In absolute terms, it is still enormous by human standards, containing tens of thousands of times the mass of Earth. But compared to Alpha Centauri A and B, it is a lightweight. Its small mass means it contributes relatively little to the total gravitational binding of the system. Nonetheless, it still matters. Its presence increases the total mass of the Alpha Centauri system slightly, and influences how gravity extends outward from the central pair. Taken together, the Alpha Centauri system has a total mass a little over 2 solar masses. From one perspective, that makes it modest. There are stars in our galaxy with tens or even hundreds of times the mass of the Sun. There are dense clusters containing thousands of stars bound together. Compared to those, Alpha Centauri is not especially heavy. But mass in physics is always relative. Compared to our solar system, which is dominated by a single star, Alpha Centauri is heavier, more complex, and capable of shaping a larger region of space through its combined gravitational influence. Mass also determines how far a system's gravity can meaningfully dominate its surroundings. While gravity technically extends infinitely, its practical influence diminishes with distance. The combined mass of Alpha Centauri means that within a certain region of space, the motion of smaller objects would be governed primarily by its stars, rather than by the gravity of the Milky Way or other nearby stars. This region is part of what defines the system's physical size. A more massive system commands a larger gravitational domain. Another way mass expresses itself is through energy output. There is a strong relationship between a star's mass and its luminosity. More massive stars have hotter cores, which increases the rate of nuclear fusion. That leads to much higher energy output. Alpha Centauri A, being slightly more massive than the Sun, is also more luminous. It emits more energy per second and appears brighter when viewed from a fixed distance. Alpha Centauri B, with its lower mass, emits less energy and shines more softly. Proxima Centauri, despite being the closest star to the Sun, is intrinsically faint because of its low mass. Its core temperature is lower, fusion proceeds more slowly, and its luminosity is only a tiny fraction of the Sun's. This contrast highlights why mass is more important than distance when it comes to intrinsic brightness. Proxima appears dim not because it is far away, but because it simply does not produce much energy. Mass also controls a star's lifespan. More massive stars live fast and die young. They burn through their nuclear fuel quickly and often end their lives in dramatic events like supernovae. Less massive stars burn slowly and steadily, lasting for billions or even trillions of years. Alpha Centauri A, with its slightly higher mass, will exhaust its hydrogen fuel sooner than the Sun. Alpha Centauri B will last longer. Proxima Centauri, with its very low mass, is expected to shine for far longer than the current age of the universe. This difference in lifespans has implications for the system as a whole. Over immense timescales, the stars will evolve at different rates. Their sizes, luminosities, and internal structures will change. These changes will alter the gravitational and radiative environment within the system. In physics, systems are rarely static. Mass determines not just the present state, but the entire evolutionary path. Comparing Alpha Centauri to the Sun in terms of mass also helps ground our understanding. The Sun contains about 99.8% of the mass of the entire solar system. The planets, asteroids, comets, and dust make up the remaining fraction. This concentration of mass creates a simple gravitational hierarchy. Planets orbit the Sun. Moons orbit planets. Everything falls neatly into place. Alpha Centauri, by contrast, spreads its mass across multiple stars. There is no single dominant center in the same way. Gravity is shared, balanced, and negotiated through motion. This shared mass distribution is what makes binary systems dynamically rich. It also complicates the formation and stability of planets. In a single star system, planets can orbit relatively undisturbed. In a multi-star system, the gravitational pull of companion stars can perturb orbits, leading to complex trajectories. Whether stable planetary orbits exist around Alpha Centauri A or B depends on mass ratios, distances, and orbital geometry. Physics provides tools to model these situations, but the outcomes are not always intuitive. Mass also connects directly to how systems respond to external influences. Passing stars, galactic tides, and molecular clouds can perturb stellar systems. A more massive system resists disruption more effectively. Alpha Centauri's central binary is tightly bound and relatively resistant to being pulled apart. Proxima's wide orbit makes it more vulnerable, but the combined mass of the system has so far kept it attached. Over billions of years, this balance has held. From another angle, mass influences how we detect and study systems. The gravitational pull of Alpha Centauri A and B on each other produces observable effects that allow mass measurement. The gravitational pull of Proxima on nearby objects can reveal the presence of planets through subtle stellar motions. In modern astrophysics, mass often reveals itself through its effects rather than its presence. We see how stars wobble, how light shifts, and how orbits behave, and from those clues we infer how heavy the system must be. As we think about bigness in physics, mass provides a different sense of scale than size or distance. Alpha Centauri is not enormous because its stars are exceptionally heavy. It is significant because it combines familiar stellar masses into a system whose total gravitational influence extends across a large region of space. It is heavy enough to bind multiple stars together, shape potential planetary systems, and persist as a stable structure within the galaxy. Instead of asking how heavy a star is, imagine approaching the question from a different angle, one that feels more geometric than gravitational. Imagine asking how much space a star actually takes up, how wide it is, how far its surface extends from its center, how much volume is enclosed inside that glowing sphere of plasma. This shift in perspective moves us from mass to radius, from how strongly a star pulls on its surroundings to how large it physically is. And while these ideas are related, they are not the same. In physics, mass and size can diverge in ways that feel counterintuitive, especially once stars enter the picture. Stellar radius is a deceptively simple term. It refers to the distance from the center of a star to its surface. For solid objects, a surface is easy to define. For stars, which are made of hot, ionized gas with no sharp boundary, the idea of a surface becomes more subtle. Physicists usually define a star's radius as the point where the gas becomes transparent enough for light to escape freely. Below that point, photons are constantly scattered and absorbed. Above it, light can travel outward into space. This boundary is not rigid, but it is consistent enough to serve as a useful definition. Using this definition, Alpha Centauri A has a radius about 1.2 times that of the Sun. Alpha Centauri B is smaller, with a radius around 0.86 times the Sun's. These differences might seem modest, but even small changes in radius translate into large changes in volume. Volume scales with the cube of the radius. If one star has a radius that is 20% larger than another, its volume is not 20% larger. It is closer to 73% larger. This cubic relationship is one of the reasons stellar size quickly becomes unintuitive. To ground this, consider the Sun. Its radius is about 696,000 kilometers. That means you could line up more than 100 Earths across its diameter. Alpha Centauri A, being about 20% larger in radius, encloses significantly more space. Its volume is roughly 1.7 times the Sun's volume. That extra space is not empty. It is filled with plasma at varying densities and temperatures, all held together by gravity and balanced against the outward pressure generated by nuclear fusion in the core. Alpha Centauri B, by contrast, is smaller than the Sun. Its radius is reduced, and its volume is only about 0.64 times the Sun's volume. Despite having nearly the same mass as the Sun, Alpha Centauri B packs that mass into a smaller volume. This means it has a higher average density. Density is mass divided by volume, and this difference highlights an important point in stellar physics. Bigger does not always mean heavier, and smaller does not always mean less massive. Stars can be compact or bloated depending on their internal structure, composition, and stage of evolution. Proxima Centauri pushes this contrast even further. Its radius is only about 14% that of the Sun. In terms of volume, that makes it incredibly small compared to Alpha Centauri A and B. Its volume is less than 1% of the Sun's volume, and yet it is still a star, sustained by nuclear fusion in its core. This illustrates how wide the range of stellar sizes can be, even within a single system. From a physics perspective, stellar radius is determined by a balance of forces. Gravity pulls matter inward, trying to compress the star. Pressure generated by nuclear fusion pushes outward, trying to make the star expand. The equilibrium between these two forces sets the star's size. For more massive stars, gravity is stronger, which tends to compress the star. At the same time, higher mass leads to higher core temperatures and faster fusion, increasing outward pressure. The resulting radius depends on which effect dominates. This is why the relationship between mass and radius is not linear. Doubling a star's mass does not double its radius. In some mass ranges, stars get larger as mass increases. In others, they get smaller. Red dwarfs, like Proxima Centauri, are relatively compact despite being fully fledged stars. Massive stars can be much larger than the Sun, but once stars exhaust their fuel and become white dwarfs, neutron stars, or black holes, their radii can shrink dramatically while retaining substantial mass. In the case of Alpha Centauri A and B, both stars are still in a stable phase of their lives known as the main sequence. They are fusing hydrogen into helium in their cores, much like the Sun. Their sizes reflect this shared evolutionary stage. Alpha Centauri A is slightly more massive, which leads to a hotter core and a slightly expanded outer envelope. Alpha Centauri B, with its lower mass, maintains a tighter structure. Volume becomes especially interesting when we consider how matter is distributed inside these stars. A star is not uniformly dense. The core is much denser than the outer layers. In the Sun, the core contains about half the Sun's mass within just a quarter of its radius. The outer layers are comparatively diffuse. This means that most of the star's volume contains relatively little mass. The same is true for Alpha Centauri A and B. Their impressive volumes do not imply solid fullness. They imply extended regions of hot, low-density plasma. This is one of the reasons stars can appear paradoxical. They are enormous, yet if you could somehow scoop up a cupful of stellar material from the outer layers, it would weigh very little. At the same time, the core is so dense and energetic that conditions there cannot be replicated on Earth. Size, volume, and density intertwine in ways that resist simple analogy. Thinking in terms of volume also helps clarify what stars are not. They are not hollow shells. They are not burning like flames. They are massive, self-gravitating spheres of plasma where energy is generated at the center and transported outward through radiation and convection. The radius marks the point where this energy finally escapes. Everything inside contributes to the star's structure, even if the outer regions dominate its visible size. When we compare the sizes of the Alpha Centauri stars to the solar system, the contrast becomes striking. The Sun's radius, enormous as it is still tiny compared to the distances between planets. Earth orbits at about 215 solar radii from the Sun's center. Neptune orbits at roughly 4,500 solar radii. If you placed Alpha Centauri A at the center of such a system, its larger radius would barely change the scale of planetary orbits. This reinforces the idea that stars, though huge by human standards, are still small compared to the spaces they inhabit. This observation becomes even more relevant when we think about the Alpha Centauri system as a whole. The distance between Alpha Centauri A and B ranges from about 11 astronomical units at closest approach to about 35 astronomical units at their farthest separation. These distances dwarf the sizes of the stars themselves. Even at their closest, the stars are separated by tens of millions of kilometers of empty space. Their physical radii barely register on that scale. From a system's perspective, the stars are compact nodes connected by gravity across vast distances. Their volumes matter for internal physics, but the structure of the system is dominated by separation, not size. This is a recurring theme in astrophysics. Objects are dense islands in a sea of emptiness. Their sizes are impressive, but the voids between them are larger still. Another important aspect of stellar radius is how it changes over time. Stars do not maintain a fixed size throughout their lives. As they exhaust hydrogen in their cores, they begin to change. The core contracts, heating up further, while the outer layers expand. Eventually, stars like Alpha Centauri A and B will become red giants, swelling to many times their current radii. During that phase, their volumes will increase dramatically, even as their masses remain nearly the same. This future evolution matters because it shows that stellar size is temporary. What we measure today is a snapshot. The current radii of the Alpha Centauri stars reflect their present balance of forces, not a permanent condition. Over billions of years, those radii will change, altering the environment within the system. Planets that might be stable today could be engulfed or destabilized in the distant future. Proxima Centauri, on the other hand, will change very little over comparable timescales. Its low mass means it burns fuel extremely slowly. Its radius will remain relatively constant for trillions of years. In this sense, Proxima's small size is linked to longevity. Smaller stars live longer lives. Larger stars live faster, more dramatic ones. Volume also plays a role in how stars interact with radiation and surrounding space. A larger surface area means more opportunity to emit energy. Alpha Centauri A's larger radius contributes to its higher luminosity alongside its higher core temperature. Alpha Centauri B's smaller radius limits its surface area and energy output. Proxima's tiny radius results in a very small emitting surface, contributing to its faintness. Yet surface area alone does not determine habitability or influence. Proxima Centauri's small size does not prevent it from hosting planets, including at least one that orbits relatively close due to the star's low luminosity. In fact, the small radius allows planets to orbit close enough to receive warmth while remaining gravitationally bound. Here again, size interacts with other properties in non-obvious ways. Returning to the idea of bigness, stellar radius answers a very specific question. It tells us how large the stars themselves are as physical objects. It does not tell us how far their influence extends. It does not tell us how massive they are. It does not tell us how far apart they are. But it provides a crucial piece of the puzzle. Without knowing the size of the stars, we cannot fully understand their density, luminosity, or evolutionary paths. Alpha Centauri, when viewed through the lens of stellar radius and volume, becomes a study in restrained variation. None of its stars are extreme outliers. None push the boundaries of known physics. Instead, they occupy familiar positions along the spectrum of stellar properties. This familiarity is precisely what makes the system valuable. It allows physicists to test theories under conditions that are close to home, both literally and conceptually. Distance inside a star system is not about empty space alone. It is about motion, balance, and the quiet negotiation between gravity and inertia that plays out over years, decades, and sometimes millennia. When we turn our attention to the separations inside the Alpha Centauri system, we are no longer asking how large the stars are as objects, but how far apart they remain while still belonging to one coherent physical structure. This shift is important, because in astrophysics, systems are defined far more by distances and motion than by the sizes of the objects themselves. Within Alpha Centauri, the most important distances are orbital distances. These are not fixed lengths like the diameter of a table or the height of a building. Orbital distances change continuously as objects move along their paths, responding to gravity while conserving energy and angular momentum. Every orbit is a compromise between falling inward and moving sideways. The result is not collapse, but repetition, motion that returns again and again to familiar configurations without ever being exactly the same. At the heart of the system, Alpha Centauri A and Alpha Centauri B orbit one another in a long, slow gravitational dance. Neither star is stationary, both move. The phrase, "one star orbiting another," is convenient but incomplete. In reality, both stars orbit a shared centre of mass. This point, invisible and empty, lies somewhere between them, closer to the more massive star but not located inside either stellar body. The distance from each star to this centre of mass depends on its mass, and the total separation between the stars depends on where they are in their orbit. The orbit of Alpha Centauri A and B is elliptical, not circular. This means the distance between them varies over time. At their closest approach, known as periastron, the stars are separated by roughly 11 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. To put that in perspective, Saturn orbits the Sun at about 9.5 astronomical units. So at their closest, Alpha Centauri A and B are separated by a distance comparable to the Sun-Saturn separation. Even then, they are extraordinarily far apart compared to their own sizes. Their stellar radii, measured in fractions of an astronomical unit, are tiny against this backdrop. At their farthest separation, called a pastron, the distance between Alpha Centauri A and B grows to about 35 astronomical units. This is farther than Neptune's average distance from the Sun. Over the course of their orbit, the stars swing between these extremes, speeding up as they approach each other and slowing down as they move apart. This behaviour follows directly from the conservation of angular momentum and the laws of gravitation described by Kepler and Newton. The orbital period of this central binary is about 80 years. That number is itself a reflection of distance. Wider orbits take longer to complete. The fact that the stars take decades to complete a single revolution tells us that the scale of their separation is large. No human lifetime can casually observe a full orbit without careful record-keeping and patience. Astronomers have been tracking the relative motion of these stars for centuries, slowly building a precise picture of their orbital parameters. From a physics perspective, these distances determine more than just motion. They define regions of stability. Around each star there exists a zone where planets could orbit stably, without being torn away or destabilized by the gravitational pull of the companion star. These regions depend sensitively on the separation between the stars and the shape of their orbit. When Alpha Centauri A and B are close together, their gravitational influence overlaps more strongly, shrinking the regions where planets could maintain stable paths. When they are farther apart, those regions expand. This introduces an important idea. Orbital distance is not just a number, it is a constraint. It sets limits on what structures can exist within a system. In the Alpha Centauri system, the varying distance between the stars means that stability is dynamic. Any planet orbiting one star must remain stable across the entire binary orbit, not just at one moment. Physics demands long-term consistency, not temporary alignment. Beyond the central binary lies Proxima Centauri, whose distance from Alpha Centauri A and B is far greater. Proxima's separation is measured not in tens of astronomical units, but in thousands. Estimates place Proxima's average distance at roughly 13,000 astronomical units from the central pair, though this value is uncertain due to the immense orbital period involved. At that distance, Proxima is more than 400 times farther from Alpha Centauri A and B than Neptune is from the Sun. This immense separation changes the character of Proxima's orbit entirely. While Alpha Centauri A and B form a tightly bound binary, Proxima is only loosely attached to the system. Its gravitational bond is weak, but still sufficient to keep it associated over long timescales. Proxima's orbital period is estimated to be on the order of hundreds of thousands of years. This means that from a human perspective, Proxima appears almost stationary relative to the central pair. Here, the meaning of orbital distance stretches again. Proxima's separation is so large that external influences become significant. Passing stars, galactic tides, and the gravitational field of the Milky Way itself all exert forces comparable to the pull of the central binary at that distance. This places Proxima in a delicate balance. It remains part of the Alpha Centauri system, but just barely. Small perturbations over millions of years could alter its orbit significantly. In physics, this kind of structure is common. Systems often have dense cores and diffuse outskirts. The Alpha Centauri system exhibits this pattern clearly. The inner region, dominated by the binary, is compact and strongly bound. The outer region, where Proxima resides, is expansive and fragile. Together, they define the system's full spatial extent. Understanding these distances also helps clarify what close means in astronomy. Alpha Centauri is the closest stellar system to our own, yet its internal distances dwarf anything we experience in daily life. Even the smallest separation between Alpha Centauri A and B represents billions of kilometers of space. And yet, in galactic terms, these distances are modest. Stars in dense clusters can orbit each other at comparable or even smaller separations. On the other hand, many stars in the galaxy are separated by distances far greater than those within Alpha Centauri. Orbital distances also determine how energy flows through the system. The stars exchange gravitational energy as they move along their elliptical paths. This exchange keeps the system stable without requiring any external input. Over time, tiny amounts of energy can be transferred to passing objects or radiated away through gravitational interactions, but the overall structure remains intact. Physics treats this as a bound system with negative total energy, meaning it would take energy input to pull it apart. There is also an important geometric aspect to these distances. Orbits are not confined to flat planes in a simple way. The orbital plane of Alpha Centauri A and B is tilted relative to our line of sight from Earth. This tilt affects how we observe their separation over time. Sometimes the stars appear closer together in the sky. Sometimes they appear farther apart. These apparent changes are projections of their true three-dimensional motion. By carefully modelling this geometry, astronomers can reconstruct the real orbital distances. This process highlights another subtle point. Distances inside star systems are not always measured directly. They are inferred through motion, angles, and time. Physics relies on consistency across observations. If the same orbital parameters explain centuries of data, the distances involved must be correct. Alpha Centauri's binary orbit is one of the best studied stellar orbits precisely because it is nearby and slow enough to track accurately. The scale of orbital distances also affects how we think about travel, even hypothetically. When people imagine journeys to Alpha Centauri, they often focus on the distance from Earth to the system, measured in light years. But once there, navigating within the system would still involve immense distances. Travelling from one star to another would take years, even at speeds far beyond current technology. The system may be close by cosmic standards, but internally it remains vast. These distances also shape the potential for interaction between stars and any surrounding material. Stellar winds, radiation, and magnetic fields weaken with distance. At the separation between Alpha Centauri A and B, these effects are minimal. The stars do not significantly influence each other's atmospheres or fusion processes. Their interaction is almost entirely gravitational. This separation ensures that each star evolves largely independently, despite being part of the same system. Comparing this to tighter binary systems reveals how distance changes behavior. In very close binaries, stars can exchange mass, distort each other's shapes, and dramatically alter their evolution. Alpha Centauri's relatively wide separation prevents these effects. The system is calm, orderly, and long-lived. Distance here acts as a stabilizing factor. As attention shifts outward again, the role of orbital distance becomes even more pronounced. Proxima's planets, for example, orbit extremely close to their star because Proxima is dim and small. Their distances are measured in fractions of an astronomical unit. This is the opposite end of the scale from Proxima's orbit around the central binary. The same system contains orbital distances ranging from millions of kilometers to trillions. Physics accommodates this range without contradiction, but intuition struggles to hold it all at once. The Alpha Centauri system, viewed through the lens of orbital distances, becomes a study in layered scale. Close distances define stellar structure. Intermediate distances define binary motion. Vast distances define loose association. Each layer obeys the same physical laws, but the outcomes differ because distance sets the context in which those laws operate. As this picture settles, it becomes clear that understanding Alpha Centauri requires thinking less about objects and more about relationships. The stars are not important only because of what they are, but because of how far apart they are and how they move together through space. These distances are what give the system its shape, its stability, and its quiet complexity. Gravity does not announce itself with sound or light. It does not have edges, surfaces, or visible structures, and yet without it, Alpha Centauri would not exist as a system at all. The stars would simply drift through the galaxy as unrelated travellers, passing near one another once and never meeting again. What makes Alpha Centauri more than a coincidence of nearby stars is gravitational binding, the condition that turns proximity into permanence and motion into structure. In physics, gravitational binding is not a vague idea. It has a precise meaning. A system is gravitationally bound when the total energy of its components is negative. That statement may sound abstract, but it captures something very concrete. Negative total energy means that the objects involved do not have enough kinetic energy to escape one another's gravitational pull. They can move, orbit, and shift positions, but they remain confined. To separate them completely, energy would have to be added from the outside. This definition is what allows physicists to decide whether something is truly a system or just a temporary arrangement. Two stars passing near each other are not a system if their trajectories carry them apart forever. Two stars orbiting a shared centre of mass are a system because gravity has locked them into a long-term relationship. Alpha Centauri qualifies as a system because its stars are gravitationally bound, not just momentarily close. At the centre of Alpha Centauri, the binding between Alpha Centauri A and Alpha Centauri B is strong and unambiguous. Their masses are comparable to the Sun's, and their separation, while large, is well within the range where gravity dominates their motion. Each star continually accelerates toward the other, but their sideways motion prevents collapse. The result is a stable orbit that has persisted for billions of years. This stability can be quantified. Using Newtonian gravity, physicists calculate the gravitational potential energy of the system and compare it to the kinetic energy of the star's motion. The numbers show that the stars are deeply bound. Their relative velocities are far below what would be required for escape. Even if a passing star nudged the system slightly, it would not be enough to break the bond between Alpha Centauri A and B. The system has a gravitational depth, a kind of energy well that the stars sit inside. This idea of a gravitational well is useful for intuition. Imagine a smooth, shallow bowl. A marble placed inside will roll around but remain trapped unless you give it a strong push. The deeper the bowl, the harder it is to remove the marble. Alpha Centauri A and B sit in a gravitational bowl shaped by their combined mass. That bowl is deep enough to keep them together across cosmic time. The situation becomes more subtle when Proxima Centauri enters the picture. Proxima is much less massive and much farther away. Its gravitational bond to the central binary is weak. In energy terms, Proxima sits near the edge of the system's gravitational well. Its orbital speed is low, and its separation is large. This places it in a marginally bound state. It is held but not tightly. Physicists care about this distinction because weakly bound objects are vulnerable. A close encounter with another star, or the cumulative effect of the Milky Way's tidal field, could alter Proxima's orbit significantly. Over millions or billions of years, such influences can add or remove energy from Proxima's motion. If enough energy is added, Proxima could escape entirely, becoming an independent star drifting through the galaxy. That possibility does not mean the system is unstable in the short term. It means that gravitational binding is not binary, it is a spectrum. Alpha Centauri A and B are strongly bound. Proxima is weakly bound. Both conditions still qualify as binding, but they behave differently over long timescales. Physics allows for this nuance, and Alpha Centauri provides a nearby example of how binding strength varies within a single system. Another important aspect of gravitational binding is that it depends on relative motion, not absolute motion. Alpha Centauri as a whole is moving rapidly through the galaxy. It orbits the centre of the Milky Way at hundreds of kilometers per second. This motion does not weaken the system's internal binding. What matters is how fast the stars move relative to one another. As long as their internal motions remain below escape velocity, the system stays intact. Escape velocity is a key concept here. It is the minimum speed an object must reach to break free from a gravitational field without further propulsion. For Earth, escape velocity is about 11.2 kilometers per second. For the Alpha Centauri binary, escape velocities depend on distance. Close to one of the stars, escape velocity is high. Farther away it drops. Proxima's orbit exists in a region where escape velocity is low, which is why its binding is fragile. Gravitational binding also explains why the Alpha Centauri system has a defined size, even though gravity technically extends forever. In practice, physicists define the system's boundary as the region within which objects remain bound over long timescales. Beyond that region, external gravitational influences dominate. For Alpha Centauri, this boundary is set not by the star's physical sizes, but by the balance between their gravity and the background gravitational field of the galaxy. This balance introduces the idea of tidal forces. The Milky Way's gravitational field is not uniform. It changes slightly across space. These differences exert tidal forces that can stretch and distort stellar systems. In dense environments, tidal forces can tear systems apart. Alpha Centauri resides in a relatively calm region of the galaxy, where tidal forces are weak. This allows even a loosely bound component like Proxima to remain attached for long periods. Binding energy also connects directly to formation. Alpha Centauri's stars likely formed from the same collapsing cloud of gas. During formation, gravitational potential energy was converted into heat and radiation, allowing the cloud to fragment and condense into multiple stars. The energy lost during this process helped to lock the system together. Without sufficient energy loss, the stars would not have become bound. Formation and binding are inseparable. Once a system is bound, gravity continues to shape its internal evolution. Orbits can change slowly through processes like angular momentum exchange, stellar winds, and interactions with surrounding matter. In Alpha Centauri, these processes are subtle. The stars are widely separated, and their winds do not interact strongly. As a result, the system evolves quietly, with little internal disruption. Gravitational binding also determines how the system responds to intruders. When another star passes nearby, its gravity can perturb the Alpha Centauri system. The effect depends on the mass of the intruder, its speed, and its distance of closest approach. For the central binary, only a very close and massive encounter would matter. For Proxima, even a more distant pass could have noticeable effects. This difference again reflects binding strength. From a physics standpoint, binding is what allows long-term prediction. If Alpha Centauri were not bound, its future configuration would be trivial. The stars would separate and the system would dissolve. Because it is bound, its future can be modelled, orbits can be projected, stability can be assessed. This predictability is one of the reasons bound systems are central to astrophysics. Binding also sets the stage for everything else we care about. Planets, if they exist, are bound to their host stars. Moons are bound to planets. Galaxies are bound collections of stars. Clusters are bound collections of galaxies. At every scale, gravity creates structure by binding matter together. Alpha Centauri is one link in this hierarchy, neither tiny nor immense, but governed by the same principles as everything else. It is worth emphasizing that gravitational binding does not imply rigidity. Bound systems are dynamic. The stars of Alpha Centauri are constantly moving. Distances change. Velocities shift. What binding guarantees is not stillness, but confinement. The motion remains organized rather than dispersive. Energy circulates rather than escapes. This idea helps reconcile two seemingly opposite facts. Alpha Centauri is vast internally, with enormous distances between its stars. At the same time, it is cohesive. Gravity bridges those distances effortlessly. In physics, distance alone does not weaken gravity beyond recognition. What matters is mass and relative motion. Given enough mass and slow enough speeds, gravity can hold together structures that span trillions of kilometers. As this understanding settles, the role of gravitational binding becomes clearer. It is the reason Alpha Centauri persists as a recognizable system. It is the reason its stars remain neighbors rather than strangers. It's the quiet condition that allows all other questions about size, distance, energy, and evolution to be meaningful. Long before numbers appear on a page, distance in astronomy begins as a problem of geometry and patience. Nothing about measuring how far away a star is can be done directly. There are no rulers long enough, no markers placed along the way, no straightforward sense of scale to rely on. Instead, physicists and astronomers are forced to work indirectly, using motion, angles, and the finite speed of light as their tools. When it comes to Alpha Centauri, our nearest stellar neighbour, this indirect approach is not just useful, it is unavoidable. The most fundamental method used to measure the distance to nearby stars is parallax. Parallax is not a complex idea, but its implications are profound. It relies on a simple geometric effect that most people have experienced without thinking about it. If you hold a finger out in front of your face and alternately close one eye and then the other, your finger appears to shift position against the background. The finger has not moved. Your point of view has. The closer the finger is to your face, the larger that apparent shift appears. The farther away it is, the smaller the shift becomes. In astronomy, the same principle applies, but the baseline is much larger. Instead of the distance between your eyes, astronomers use the diameter of Earth's orbit around the Sun. As Earth moves from one side of its orbit to the other, over the course of 6 months, nearby stars appear to shift slightly relative to much more distant background stars. This shift is tiny, far smaller than what the human eye can detect unaided, but with precise instruments, it can be measured. The angle of this shift is called the parallax angle. It is defined as half the total apparent shift observed over 6 months. From this angle, simple trigonometry can be used to calculate the star's distance. The smaller the parallax angle, the farther away the star must be. Alpha Centauri has one of the largest stellar parallax angles ever measured, precisely because it is so close by astronomical standards. To make this method practical, astronomers define a unit of distance called the parsec. 1 parsec is the distance at which a star would have a parallax angle of exactly 1 arcsecond. An arcsecond is an extremely small angle, equal to 1/3600th of a degree. For context, the full moon spans about 1/800 arcseconds in the sky. A parallax of 1 arcsecond is barely detectable even with modern equipment. Alpha Centauri has a parallax angle of about 0.76 arcseconds. Using the definition of a parsec, this places Alpha Centauri at a distance of roughly 1.3 parsecs, which corresponds to about 4.37 light years. This measurement is not a guess. It is the result of repeated observations refined over decades, using increasingly precise instruments. The distance to Alpha Centauri is one of the best-known stellar distances in astronomy. Parallax measurements require extraordinary care. Earth's atmosphere distorts incoming light. Instruments flex with temperature changes. Stars themselves move slightly over time due to their motion through the galaxy. All of these effects must be accounted for. When astronomers say they have measured a parallax, they mean they have modelled and subtracted every other source of apparent motion until only the geometric effect remains. Because parallax angles decrease rapidly with distance, this method has a practical limit. Beyond a few thousand light years, parallax becomes too small to measure accurately from Earth. This limitation shaped astronomy for centuries. For a long time, Alpha Centauri and a handful of other nearby stars were among the only ones with reliably known distances. Everything farther away had to be measured using different techniques. That is where light itself becomes the next tool. Light is not instantaneous. It travels at a finite speed, approximately 290,792 kilometers per second in a vacuum. This speed is constant and universal, making it one of the most reliable yardsticks in physics. When astronomers measure distances in light years, they are not introducing a metaphor. They're using a physical quantity that ties space directly to time. A light year is the distance light travels in 1 year. That works out to about 9.46 trillion kilometers. When we say Alpha Centauri is 4.37 light years away, we are saying that the light entering our telescopes today left those stars more than 4 years ago. The photons have been travelling through interstellar space ever since, unaffected by most matter, carrying information about the star's state at the moment they were emitted. This has an important implication that is easy to overlook. Distance measurement in astronomy is always also a look into the past. The farther away an object is, the older the information we receive. In the case of Alpha Centauri, the delay is short by cosmic standards, but it is still real. If something dramatic were to happen in the system today, we would not know about it for years. Light allows astronomers to measure distance in more subtle ways as well. The brightness of a star as seen from Earth depends on 2 main factors: how much energy the star emits and how far away it is. If the intrinsic luminosity of a star can be determined independently, then the observed brightness can be used to calculate distance. This relationship follows an inverse square law. Double the distance, and the brightness drops by a factor of 4. For Alpha Centauri, this method serves as a consistency check rather than a primary measurement. Because Alpha Centauri's distance is already known from Parallax, astronomers can compare its observed brightness to its expected luminosity based on stellar models. The agreement between these values provides confidence in both the distance measurement and the models themselves. Light also carries spectral information. By spreading starlight into a spectrum, astronomers can identify the elements present in a star's atmosphere and determine its temperature and surface gravity. These properties are linked to mass and radius, which in turn influence luminosity. All of these pieces fit together. Distance, mass, size, and brightness are not independent facts. They form a connected web, and Alpha Centauri sits at a point where many of these connections can be tested directly. Another light-based method relevant to distance measurement is called Doppler shift. As a star moves toward or away from us, the wavelengths of its emitted light shift slightly. Motion toward us compresses the wavelengths, shifting them toward the blue end of the spectrum. Motion away stretches them, shifting them toward the red. By measuring these shifts, astronomers can determine a star's radial velocity, its motion along our line of sight. For Alpha Centauri, Doppler measurements reveal how the stars move relative to the Sun. Combined with proper motion measurements, which track motion across the sky, astronomers can reconstruct the full, three-dimensional motion of the system. This does not directly give distance, but it provides context. A star with large proper motion is often nearby, while distant stars tend to show smaller apparent motion. Alpha Centauri exhibits one of the largest proper motions of any bright star. It visibly shifts its position against the background of distant stars over time. This was one of the earliest clues that it was close to us. Parallax confirmed this proximity quantitatively, but the large proper motion already hinted at a short distance. Light also plays a role in defining the limits of distance measurement. There is a horizon beyond which light has not had time to reach us since the beginning of the universe. This cosmic light horizon sets the maximum observable distance. Alpha Centauri, of course, lies comfortably within this limit, but understanding light as a messenger reminds us that distance measurement is constrained by the finite age and structure of the universe. The act of measuring distance using light and parallax also depends on time. Parallax requires observations spread over months or years. Proper motion requires decades of tracking. Refining measurements involves repeated cycles of observation, calibration, and correction. Physics provides the framework, but time provides the data. Alpha Centauri's distance is well known precisely because astronomers have had centuries to observe it. What makes Alpha Centauri especially valuable is that it sits at the intersection of geometric and light-based methods. Its distance is close enough for parallax to work cleanly. Its stars are bright enough for detailed spectral analysis. Its motion is large enough to track accurately. Few systems offer all of these advantages at once. As a result, Alpha Centauri serves as a benchmark. Other distance measurement techniques are often tested and calibrated against nearby stars like it. It is also worth considering what distance measurement does not tell us. Knowing that Alpha Centauri is 437 light-years away does not tell us how large the system is internally. It does not tell us how massive the stars are. It does not tell us how gravity binds them together. Distance is one dimension of understanding, not a complete description. Physics advances by combining dimensions, not isolating them. Even the concept of distance itself becomes subtle at larger scales. In expanding space, distance depends on how and when you measure it. Light emitted in the past travelled through a universe that was slightly smaller than it is today. For Alpha Centauri, this effect is negligible. The expansion of space over 4 years is insignificant, but the principles are the same. Distance is not always a static quantity. It can depend on cosmological context. In practical terms, measuring distance to Alpha Centauri anchors our sense of scale. It tells us how far away our nearest stellar neighbour really is, not as a vague idea, but as a precise physical quantity. This distance sets the baseline for everything else. Travel time estimates, communication delays, comparisons with other stars all depend on it. Without parallax and the finite speed of light, Alpha Centauri would remain a point of light with unknown depth. With them, it becomes a place with coordinates, a location in three-dimensional space that can be plotted, modelled, and revisited in calculations again and again. Physics transforms uncertainty into structure not by simplifying the universe, but by measuring it carefully. As attention continues to shift outward, distance measurement becomes the bridge between local systems and the broader galaxy. Parallax defines the nearby universe. Light-based methods extend that reach farther and farther. Alpha Centauri stands near the beginning of that ladder, close enough to measure directly, far enough to remind us how quickly scale escapes everyday intuition. A different way of thinking about distance becomes necessary once the numbers grow beyond anything the human body or daily experience can comfortably handle. Kilometers stop being useful. Even millions of kilometers lose their meaning. At that point, physics does something very practical. It changes units. Not to be poetic, not to be dramatic, but to keep calculations honest and manageable. This is where the Lightyear enters the discussion, not as a metaphor, not as a figure of speech, but as a strict physical unit grounded in measurement, speed, and time. A light year is simply the distance light travels in 1 year through a vacuum. Nothing more than that. There is no implication of travel, storytelling, or drama built into the definition. It does not describe how long something lasts. It describes how far something is. The confusion arises because the word year sounds like time, and our brains naturally lean toward narrative interpretations. Physics does not. In physics, a light year is a ruler, not a clock. To understand why this unit exists at all, it helps to look at the speed of a light itself. Light travels at a constant speed in a vacuum, approximately 209,9792 km per second. This number is not approximate because of experimental uncertainty. It is exact by definition in modern physics. The meter itself is defined in terms of how far light travels in a fraction of a second. Light speed is woven directly into the structure of our measurement system. Over the course of 1 second, light travels nearly 300,000 kilometers. In 1 minute, it travels about 18 million kilometers. In 1 hour, it covers over 1 billion kilometers. Over an entire year, accounting for the length of a year used in astronomy, light travels roughly 9.46 trillion kilometers. That distance is what we call 1 light year. Writing that number out in full quickly becomes impractical. Even reading it provides no intuitive sense of scale. That is why physics compresses it into a single unit. When astronomers say Alpha Centauri is about 4.37 light-years away, they are not being vague. They are being precise. They are stating that the distance between Earth and Alpha Centauri is roughly 4.37 times 9.46 trillion kilometers. Using light years keeps equations readable and comparisons meaningful. Saying one star is 5 light-years away and another is 50 light-years away immediately communicates relative distance without drowning the discussion in zeros. This is not a storytelling choice, it is a mathematical one. What makes the light year especially useful is that it links distance directly to a fundamental constant. Light speed is not arbitrary. It is the maximum speed at which information can travel through space. No signal, no force, no influence can propagate faster. This means that distance measured in light years also encodes a limit on causality. If something happens in Alpha Centauri today, it cannot affect Earth for more than 4 years. That delay is not technological. It is built into the structure of space-time. This connection between distance and information is why light years feel different from kilometers. Kilometers are passive. They describe separation, but say nothing about interaction. Light years immediately tell you something about communication, observation, and cause and effect. They tell you how long the universe takes to let one place know what has happened in another. Despite this, a light year remains a distance, not a duration. When light travels, it does not experience time the way we do. According to relativity, light does not have a rest frame. From the photon's perspective, if such a perspective can be meaningfully described, emission and absorption are not separated by time. The year in light year belongs entirely to our frame of reference, not to the light itself. This is one reason physicists are careful when discussing light years. They are not talking about how long something takes to happen in an absolute sense. They're talking about how far apart events are in space-time, measured using a constant speed as a conversion factor. For Alpha Centauri, the use of light years places it firmly in the category of nearby stars. In the context of the Milky Way, which spans roughly 100,000 light-years in diameter, a distance of 4.37 light-years is small. On a galactic map, Alpha Centauri sits almost on our doorstep. There are stars tens of thousands of light-years away whose light began its journey before human civilization existed. Yet calling Alpha Centauri nearby does not make it practically close. This is where intuition often fails. 4 light-years is short compared to the size of the galaxy, but enormous compared to anything we can traverse. Even travelling at 10% the speed of light, which is far beyond current engineering capability, the journey would take more than 40 years, not counting acceleration or deceleration. This gap between cosmic proximity and practical reach is precisely why light years are necessary. They allow physics to remain consistent even when human experience falls away. The unit does not pretend that Alpha Centauri is reachable. It simply states how space is structured. Light years also allow physicists to stack scales cleanly. Distances within planetary systems are measured in astronomical units. Distances between stars are measured in light years or parsecs. Distances between galaxies are measured in millions or billions of light years. Each step up represents a shift not just in size, but in the kinds of processes that dominate. Within a few light years, individual stars and their systems matter. At hundreds of light years, stellar populations and clusters become relevant. At millions of light years, galaxies and their interactions dominate. At billions of light years, cosmology takes over and the expansion of space itself becomes unavoidable. The light year scales naturally across these regimes. Another reason the light year is a physical unit rather than a metaphor is that it appears directly in equations. When physicists calculate luminosity, flux, or radiation intensity, distance enters the equation squared. Whether that distance is expressed in meters, kilometers, or light years does not change the physics, but using light years often simplifies interpretation. A star twice as far away in light years appears 4 times dimmer. The unit carries that relationship cleanly. Light years also appear when discussing horizons. There is a maximum distance from which light has had time to reach us since the beginning of the universe. This sets the size of the observable universe, measured in billions of light years. This horizon is not about how long the universe has existed in isolation. It is about how far information has been able to travel. Again, light years encode both distance and causal structure. In the case of Alpha Centauri, the light year tells us that we are seeing the system slightly out of date. The stars we observe today are as they were more than 4 years ago. Their positions, brightness, and activity are frozen in the light that has already arrived. Any changes since then remain unseen. This delay is short enough to feel almost negligible, but it is real. Physics does not treat it as symbolic. It treats it as a measurable lag. This has practical consequences for observation. When astronomers model the motion of Alpha Centauri, they must account for light travel time. The apparent position of the stars in the sky reflects where they were when the light was emitted, not where they are now in an absolute sense. For nearby stars like Alpha Centauri, the correction is small but necessary for high-precision work. Light years also help avoid misleading mental shortcuts. If distance were always expressed in time, people might assume travel is simply a matter of waiting. If distance were always expressed in kilometers, people might underestimate how quickly numbers grow. The Lightyear strikes a balance. It anchors distance to a fundamental speed while remaining clearly spatial. In physics, metaphors are dangerous when they begin to replace definitions. The Lightyear survives precisely because it does not require metaphor to function. It is defined, measurable, and consistent. It appears in calculations whether or not anyone finds it intuitive. Alpha Centauri's distance in light years also sets a boundary between direct and indirect measurement techniques. Parallax works reliably within a few hundred light years. Beyond that, astronomers must rely on standard candles, redshift measurements, and cosmological models. Alpha Centauri lies comfortably within the parallax regime, making its light-year distance one of the most solid numbers in stellar astronomy. This reliability matters. Many cosmic distances are model-dependent. They rely on assumptions about stellar evolution or cosmic expansion. Alpha Centauri's distance does not. It is anchored to geometry and light speed. That makes it a reference point. Other distances are checked against systems like Alpha Centauri to ensure consistency. Thinking of light years as physical quantities also clarifies why scale comparisons matter so much. Saying Alpha Centauri is 4 light years away does not mean much until you compare it to something else. Earth to Sun is 8 light minutes. Earth to Jupiter is about 40 light minutes. Earth to Pluto is roughly 5.5 light hours. Alpha Centauri sits more than 4 light years away. Each step up increases distance by orders of magnitude, not by smooth increments. These jumps in scale are where intuition collapses, but physics remains comfortable. The equations do not care whether the distance is measured in meters or light years. They behave the same. It is our understanding that struggles, not the math. By treating the light year as a physical unit rather than a metaphor, Alpha Centauri becomes easier to place correctly in the universe. It is not unimaginably far in every sense. It is not close in any practical sense. It occupies a specific, measurable position in space, separated from us by a distance that light takes a little over 4 years to cross. Brightness is one of the first things we notice about stars, yet it is also one of the easiest properties to misunderstand. A bright star in the sky feels powerful, dominant, perhaps even large. A faint one feels distant or small. Physics quickly strips those impressions away. Brightness as seen from Earth is only an appearance. What actually matters when comparing stars is luminosity, the total amount of energy a star produces every second, regardless of where it is observed from. When we talk about the energy output of Alpha Centauri, we're no longer dealing with perception at all. We're dealing with power measured precisely, governed by nuclear physics, and tied directly to mass, size, and internal structure. Luminosity is defined as the total energy emitted by a star per unit time. In physics, energy per unit time is power, measured in watts. The sun's luminosity is about 3.26 watts. That number is so large it is rarely written out in full. Instead, physicists use it as a reference unit called 1 solar luminosity. This allows other stars to be compared directly to the sun without drowning in numbers. When we say a star has a luminosity of 2 solar luminosities, we mean it produces twice as much energy per second as the sun. When we say half a solar luminosity, we mean half as much. Alpha Centauri is not one luminous object but several, each with its own energy output. Alpha Centauri A, Alpha Centauri B, and Proxima Centauri all generate energy through nuclear fusion, but they do so at very different rates. Their luminosities reflect differences in mass, radius, core temperature, and fusion efficiency. Understanding these differences is essential for understanding how big Alpha Centauri is in an energetic sense, not just a spatial one. Alpha Centauri A is the most luminous member of the system. Its luminosity is about 1.5 times that of the Sun. This means that every second Alpha Centauri A releases roughly 50% more energy than the Sun does. This higher energy output is not dramatic enough to place it among extreme stars, but it is significant. The reason lies in its slightly greater mass and larger radius. With more mass, gravity compresses the core more strongly, raising the temperature and pressure. Fusion reactions proceed at a faster rate. Even a modest increase in core temperature leads to a disproportionately large increase in energy production, because fusion rates are extremely sensitive to temperature. This sensitivity is one of the most important ideas in stellar physics. Fusion does not scale linearly. A small change in conditions leads to a large change in output. That is why stars do not form a smooth continuum of luminosities. They cluster into distinct categories. Alpha Centauri A sits comfortably above the Sun, producing more energy but still operating under the same physical processes. Alpha Centauri B tells a different story. Its luminosity is only about 0.5 times that of the Sun. Despite having nearly the same mass as the Sun, it produces only about half as much energy per second. This is not because it is inefficient, but because its slightly lower mass leads to a cooler core. Fusion reactions slow down. The star settles into a lower luminosity equilibrium. The difference between Alpha Centauri A and B illustrates just how finely balanced stellar energy production is. A small difference in mass leads to a large difference in luminosity. Proxima Centauri occupies an entirely different regime. Its luminosity is roughly 0.0017 times that of the Sun. In other words, it produces less than 0.2% of the Sun's energy output. This extreme faintness is not due to distance. Proxima is closer to Earth than any other star beyond the Sun. It is faint because it is small and cool. Its core temperature is much lower. Fusion proceeds slowly. Energy trickles out rather than floods. This enormous spread in luminosity within a single system highlights a key point. Energy output does not scale directly with size or proximity. It scales with mass and internal conditions. Alpha Centauri contains stars that differ in luminosity by nearly 3 orders of magnitude, yet all are bound together by gravity and formed from the same region of space. Luminosity is also closely tied to surface temperature. The energy produced in a star's core must eventually escape through its surface. The rate at which energy can be radiated away depends on surface area and temperature. This relationship is described by the Stefan-Boltzmann law, which states that the energy emitted per unit area of a black body increases with the fourth power of temperature. This means temperature matters enormously. A small increase in surface temperature leads to a large increase in energy output. Alpha Centauri A has a surface temperature slightly higher than the Sun's. Combined with its larger radius, this gives it a greater total emitting surface and higher luminosity. Alpha Centauri B has a cooler surface and smaller radius, reducing both the energy emitted per square meter and the total emitting area. Proxima Centauri has a much cooler surface, drastically limiting its energy output despite radiating steadily. From a physics standpoint, luminosity is not just a property of the star itself. It shapes the environment around the star. The amount of energy flowing outward determines the temperature of surrounding space, the behavior of stellar winds, and the potential conditions on orbiting planets. In Alpha Centauri, each star creates a distinct energetic domain. If a planet orbits Alpha Centauri A, it will receive more energy at a given distance than a planet orbiting the Sun would. To receive the same amount of energy as Earth does from the Sun, a planet would need to orbit Alpha Centauri A farther out. Around Alpha Centauri B, that equivalent distance would be closer in. Around Proxima Centauri, it would be extremely close. These differences are not incidental. They define where stable climates might exist, how atmospheres behave, and how radiation interacts with matter. Luminosity also changes over time. Stars do not produce a constant amount of energy throughout their lives. As hydrogen is converted into helium in the core's composition changes. Over billions of years, this alters the balance of pressure and temperature. For stars like Alpha Centauri A and B, luminosity gradually increases over time. The Sun itself is about 30% more luminous now than it was when it formed. Alpha Centauri A, being slightly more massive, evolves faster. Its luminosity will increase more quickly, This gradual brightening matters because it affects the long-term stability of planetary environments. A system's energetic size is not fixed. It grows. The Alpha Centauri system today is not energetically identical to what it was billions of years ago, and it will not remain so indefinitely. Physics treats luminosity as a dynamic quantity, not a static one. Another important aspect of energy output is variability. Stars are not perfectly steady light bulbs. They have magnetic cycles, surface activity, flares, and oscillations. Alpha Centauri A and B exhibit magnetic activity similar to the Sun, including star spots and activity cycles. These variations cause small fluctuations in luminosity. Proxima Centauri is far more active relative to its size, producing frequent flares that can briefly increase its energy output dramatically, especially at high energy wavelengths. These variations remind us that luminosity is usually quoted as an average. The instantaneous energy output can differ from moment to moment. Over long timescales, averages matter. Over short timescales, spikes and dips can dominate local conditions. For planets, especially those orbiting close to low luminosity stars like Proxima, these fluctuations can be as important as the average output. From the perspective of system size, energy output defines a kind of invisible boundary. The influence of a star's radiation weakens with distance. At some point it becomes negligible compared to background radiation from other stars and the galaxy itself. The distance at which a star's luminosity meaningfully affects its surroundings depends on how much energy it produces. Alpha Centauri A's energetic reach extends farther than Alpha Centauri B's. Proxima's energetic influence drops off quickly. This energetic reach is different from gravitational reach. Gravity depends on mass and falls off with distance squared. Radiation intensity also falls off with distance squared, but its effects are different. Gravity pulls matter inward, radiation pushes outward, heats surfaces, and drives chemical reactions. In a system like Alpha Centauri, these two influences overlap but do not coincide exactly. A region might be gravitationally dominated by a star while receiving little radiation from it, or vice versa. Energy output also connects directly to detectability. The reason Alpha Centauri A and B appear bright in the sky is not just because they are close, but because they are relatively luminous. Proxima, despite being closer, is invisible to the naked eye because its luminosity is so low. This difference underscores why luminosity must be separated from distance when discussing size. Brightness alone tells us very little. In astrophysics, luminosity is often used as a proxy for mass because of the mass-luminosity relationship for main sequence stars. More massive stars are generally more luminous. This relationship is not exact, but it is strong. For Alpha Centauri, the luminosities of A and B align well with their measured masses, reinforcing confidence in both measurements. Proxima deviates from a simple extrapolation because very low-mass stars follow a different regime, where energy transport and fusion behave differently. Energy output also determines how stars age. A star that produces more energy consumes its nuclear fuel faster. Alpha Centauri A, being more luminous than the Sun, will exhaust its hydrogen sooner. Alpha Centauri B will last longer. Proxima Centauri will last far longer than either. In this sense, luminosity is tied directly to time. Brighter stars live shorter lives. Dimmer stars endure. When considering how big Alpha Centauri is, energetically speaking, the system's total luminosity is the sum of its parts. Combined, Alpha Centauri A and B produce about twice the Sun's energy output. Proxima adds a small amount. The total system luminosity is therefore a bit over 2 solar luminosities. That makes Alpha Centauri a modest but significant energy source in our local region of the galaxy. Compared to massive stars or clusters, this output is small. Compared to our solar system, it is large. This again illustrates that bigness in physics is always comparative. There is no absolute threshold where something becomes big. There are only relationships. Energy output also shapes how we interpret distance measurements. The inverse square law linking luminosity and observed brightness is fundamental. If Alpha Centauri were twice as far away, it would appear 4 times dimmer. If it were half as far, it would appear 4 times brighter. Because we know its luminosity from stellar physics and its distance from parallax, these relationships reinforce one another. This cross-checking is a cornerstone of astrophysical measurement. As attention continues to widen, energy output becomes one of the bridges between internal stellar physics and large-scale structure. Luminosity influences how stars populate galaxies, how galaxies shine, and how cosmic history unfolds. Alpha Centauri sits at the small end of this ladder, but it obeys the same rules as everything else. Perspective changes everything once scale enters the conversation. Numbers alone rarely succeed at conveying how large something is, especially when those numbers describe astronomical distances and structures that have no direct counterpart in everyday life. Physics is aware of this limitation, which is why comparison is such a powerful tool. When Alpha Centauri is set beside the solar system, not metaphorically but structurally, the differences and similarities begin to clarify what big actually means in a physical sense. This comparison does not rely on imagination or analogy. It relies on matching quantities, forces, distances, and motions that are governed by the same laws. The solar system provides a natural reference because it is the only star system we know in detail from the inside. We know the sun's mass, radius, luminosity, and age. We know the orbital distances of the planets. We know how gravity structures the system, where stability exists and where it breaks down. When Alpha Centauri is compared to this familiar framework, it stops being an abstract neighbour and becomes a system that can be measured against something concrete. At the centre of the solar system sits the Sun, containing roughly 99.8% of the system's total mass. Everything else, planets, moons, asteroids, comets, and dust, contributes only a tiny fraction. This extreme mass concentration creates a simple hierarchy. The Sun dominates gravitationally, planets orbit the Sun, moons orbit planets. The structure is nested and orderly. Orbital planes are roughly aligned. Long-term stability is high because there is only one major gravitational authority. Alpha Centauri does not follow this pattern. Instead of one dominant central mass, it has 2. Alpha Centauri A and Alpha Centauri B share control of the system's inner region. Their masses are comparable, and neither star can be treated as a minor perturbation to the other. Both orbit a shared centre of mass. This immediately makes the system more complex. There is no equivalent situation in the solar system, where no 2 objects of comparable mass orbit one another in this way. If the Sun were paired with another star of similar mass at a distance comparable to Saturn's orbit, the solar system would look very different. Planetary orbits would be strongly perturbed. Some planets might not exist at all. Others would follow elongated, unstable paths. The calm, layered structure we observe would be replaced by a more dynamic environment. This thought experiment highlights the first major difference in scale between Alpha Centauri and the solar system. It is not just larger, it is organised differently. Distance is the next critical factor. The outer boundary of the solar system is not sharply defined, but the region dominated by the Sun's gravity extends far beyond the orbit of Neptune. The Kuiper belt stretches from about 30 to 50 astronomical units. Beyond that lies the Oort cloud, a vast spherical distribution of icy bodies that may extend tens of thousands of astronomical units from the Sun. Objects in the outer Oort cloud are only loosely bound to the Sun, vulnerable to gravitational disturbances from passing stars. In terms of sheer spatial extent, the solar system is enormous. If the Oort cloud extends out to 50,000 astronomical units, then the Sun's gravitational influence covers a region far larger than the distance between Alpha Centauri A and B at their widest separation. This might suggest that the solar system is bigger than Alpha Centauri. But physics requires more precision than that. The key difference lies in mass distribution. The solar system's outer regions contain very little mass. The Oort cloud is vast but sparse. Its total mass is tiny compared to the Sun. Alpha Centauri's outer region, represented by Proxima Centauri's orbit, contains an entire star. Even though Proxima is small, it outweighs all the planets and minor bodies of the solar system combined. This difference matters because gravitational structure depends not just on distance, but on how much mass occupies that distance. Looking inward again, planetary scales provide another comparison point. Earth orbits the Sun at 1 astronomical unit. Jupiter orbits at about 5.2 astronomical units. Neptune orbits at about 30 astronomical units. These distances define the solar system's core architecture. In Alpha Centauri, the separation between Alpha Centauri A and B ranges from roughly 11 to 35 astronomical units. This places their orbits squarely within the scale of the solar system's planetary region. If Alpha Centauri A were the Sun, and Alpha Centauri B were a massive companion star, its orbit would sweep through the region occupied by the giant planets. The presence of such a companion would radically alter the solar system's structure. This comparison underscores how much larger Alpha Centauri's internal separations are compared to the sizes of the stars themselves, and how those separations overlap with the distances that define planetary systems. Another point of comparison involves orbital periods. Earth takes 1 year to orbit the Sun, Jupiter takes about 12 years, Neptune takes about 165 years, Alpha Centauri A and B take about 80 years to orbit one another. This places their orbital period between that of Saturn and Uranus if we were to force an analogy. But the analogy breaks down quickly because in the solar system, planets orbit a much more massive central body. In Alpha Centauri, the stars orbit each other as equals. Time, as expressed through orbital periods, reflects scale. Longer periods generally indicate larger orbits or weaker central gravitational dominance. Alpha Centauri's 80-year period signals a system that is wide but still tightly bound. It occupies an intermediate scale, larger than most planetary orbits, but far smaller than the distances between unrelated stars. Energy output also plays a role in comparison. The Sun is the sole significant energy source in the solar system. All planets receive energy from it. Alpha Centauri has 2 major energy sources in its inner region. Alpha Centauri A and B both emit significant radiation. Any planet orbiting within the system would experience a more complex radiation environment, with energy contributions that vary over time as the stars move relative to one another. This difference in energetic structure contributes to a sense of scale that goes beyond distance. The solar system's energy landscape is simple and centralized. Alpha Centauri's is distributed and dynamic. From a physics standpoint, this increases the system's effective complexity without necessarily increasing its physical size in every dimension. Comparing gravitational binding further sharpens the picture. The solar system is bound primarily by the Sun's gravity. The Alpha Centauri system is bound by the combined gravity of multiple stars. The depth of the gravitational well in the inner Alpha Centauri system is comparable to that of the solar system's inner regions, but its shape is different. Instead of a single deep well, there is a more complex potential shaped by 2 moving masses. This has implications for stability and long-term evolution. The solar system's architecture has remained relatively unchanged for billions of years. Alpha Centauri's architecture is also stable, but stability arises from balance rather than dominance. The star's masses, distances, and velocities are finely tuned to avoid close encounters or ejection. Physics allows both arrangements, but they represent different solutions to the same gravitational equations. Proxima Centauri adds another comparison layer. Its separation from the central pair is on the order of thousands of astronomical units. This places it in a regime similar to the outer Oort cloud in the solar system, but again, the analogy is limited. Proxima is not a cloud of debris, it is a star with its own planets, radiation, and magnetic activity. Its presence stretches the Alpha Centauri system's scale far beyond what the solar system contains in terms of mass and energy at comparable distances. Motion through the galaxy also enters the comparison. Both the solar system and Alpha Centauri orbit the centre of the Milky Way. Their velocities and paths are similar, reflecting their shared membership in the galaxy's disk. On this scale, both systems are small components of a much larger structure. Neither dominates its surroundings beyond a tiny region. This shared galactic context helps normalize the comparison. Alpha Centauri is not a special case. It is one of many stellar systems shaped by the same forces. Another useful comparison involves emptiness. The solar system feels crowded because we know its contents in detail. Alpha Centauri feels empty because we know less about it. Physically, both systems are dominated by empty space. The distances between planets in the solar system are vast compared to the sizes of the planets themselves. The distances between stars in Alpha Centauri are even larger by comparison. In both cases, matter occupies only a tiny fraction of the available volume. This observation reinforces a central theme. Size in physics is not about how much stuff there is, it is about how that stuff is arranged. Alpha Centauri contains more massive objects spread over larger distances than the solar system, but both systems are overwhelmingly empty. Their structures are defined by relationships, not by density. When comparing the two systems, it is also important to recognize scale layering. The solar system is a single-star planetary system, embedded in a larger galactic environment. Alpha Centauri is a multi-star system that may contain its own planetary systems, also embedded in the same galactic environment. The solar system's scale ends where the Sun's gravitational influence fades. Alpha Centauri's scale extends farther because it includes multiple stars, yet neither system exists in isolation. Over long timescales, passing stars can perturb both. Galactic tides can reshape outer regions. The difference is one of degree, not kind. Alpha Centauri's extended structure makes it slightly more susceptible to external influences at its fringes, while its inner core remains robust. All of these comparisons point toward a conclusion that resists simple phrasing. Alpha Centauri is not simply bigger or smaller than the solar system. It is larger in some respects, more complex in others, and comparable in yet others. Its stars are similar in size and mass to the Sun. Its internal distances overlap with planetary scales. Its outer reach exceeds that of the solar system in terms of massive objects. Its energy output is roughly double that of the Sun alone. By placing Alpha Centauri beside the solar system in this way, physics strips away the temptation to rank systems as large or small in absolute terms. Instead, it reveals a spectrum of structures built from the same ingredients: gravity, mass, distance, energy, and time combine in different proportions to produce systems that are stable, dynamic, and persistent. Space does not arrange stars neatly, like points on graph paper or beads on a string. Instead, star systems are scattered through the galaxy with separations that are vast, uneven, and governed by probability rather than design. When we talk about the physical separation between star systems, we are no longer focused on what happens inside a system like Alpha Centauri or the solar system. We are stepping outside those gravitational islands and looking at the distances that exist between them, distances so large that even the concept of nearby begins to lose its everyday meaning. From a physics standpoint, the separation between star systems is one of the defining features of the universe on humanly accessible scales. Stars are not packed together tightly. They occupy an environment that is overwhelmingly empty. Matter is concentrated into discrete systems, while the space between them contains only a thin scattering of gas, dust, radiation, and fields. This separation is not accidental. It is the outcome of how galaxies form, evolve and balance gravity against motion over billions of years. In the region of the Milky Way where the Sun and Alpha Centauri reside, the average distance between star systems is several light years. Alpha Centauri is unusually close at just over 4 light years away. Many of the next nearest stars are 6, 8 or 10 light years distant. Beyond that, distances continue to grow. Even in what astronomers consider a relatively dense stellar neighbourhood, stars are separated by trillions of kilometres. To appreciate this physically, it helps to think in terms of number density rather than isolated distances. In the local region of the Milky Way, there are roughly 0.1 to 0.2 stars per cubic parsec. A cubic parsec is a volume measuring about 3.26 light-years on each side. That means that, on average, a region of space large enough to enclose several star systems still contains mostly nothing. The typical separation between stars emerges naturally from this low density. This low density has profound consequences. Gravity between star systems is weak compared to the gravity inside them. The gravitational pull between the Sun and Alpha Centauri exists, but it is negligible compared to the gravitational forces binding planets to stars or stars to each other within a system. As a result, star systems behave like largely independent entities, moving through the galaxy on long, smooth trajectories without strongly influencing one another most of the time. The separation between systems is not static. Stars move. The Sun and Alpha Centauri are not fixed points in space. Both are orbiting the centre of the Milky Way, completing one galactic orbit roughly every 230 million years. Their relative positions change slowly over time. Millions of years ago, Alpha Centauri was farther away. Millions of years from now, it will be farther away again. For a period, it happens to be close. This closeness is temporary on cosmic timescales. This motion means that physical separation must always be understood as a function of time. When physicists say Alpha Centauri is 4.37 light-years away, they mean right now within a small margin of uncertainty. That distance is not permanent. It drifts as both systems move through the galactic gravitational field. Over long enough timescales, entirely different stars will become our nearest neighbours. Despite this motion, encounters between star systems are extremely rare. Even when stars pass close to one another by astronomical standards, they are still separated by distances far greater than the size of their planetary systems. A close stellar encounter might occur at a distance of a fraction of a light-year, which is still tens of thousands of astronomical units. Such encounters can disturb the outermost regions of star systems like Oort clouds, but they almost never affect inner planets. This rarity of interaction reinforces the importance of separation. Star systems are isolated not because of barriers or forces pushing them apart, but because space itself is vast and matter is sparse. Gravity shapes systems locally, but it does not collapse the galaxy into a single dense cluster, because stars possess significant orbital motion around the galactic centre. That motion balances gravitational attraction, spreading systems out over enormous volumes. The separation between star systems also reflects conditions during star formation. Stars form in molecular clouds, dense regions of gas and dust. These clouds fragment into cores that collapse under gravity. The spacing between those cores sets the initial separation between star systems. Over time, gravitational interactions and galactic dynamics modify these separations, but the initial spacing leaves a lasting imprint. In dense star clusters, separations are much smaller. Stars can be separated by fractions of a light-year or even less. In such environments, interactions are common. Systems are disrupted. Stars are ejected. Planetary systems struggle to remain stable. Alpha Centauri does not live in such an environment. It resides in the galactic disk, far from dense clusters, in a region where separations are large and interactions are infrequent. This context helps explain why Alpha Centauri has remained intact for billions of years. The physical separation between systems acts as a protective factor. Without frequent close encounters, gravitational binding inside systems is preserved. The wide gaps between stars act like buffers, reducing the chances of disruptive interactions. From another angle, separation defines communication limits. Because information cannot travel faster than light, the distance between star systems sets a hard, lower bound on communication time. A signal sent from Earth to Alpha Centauri takes over 4 years to arrive. A reply takes another 4. Any exchange is stretched across nearly a decade. For more distant systems, delays grow rapidly. This is not a technological limitation. It is a physical one. The separation also defines energetic independence. Radiation from stars spreads out and weakens with distance. By the time light from Alpha Centauri reaches the solar system, it is faint compared to the sun's radiation. The energy budgets of star systems are largely self-contained. Each system is dominated by its own stars, not by its neighbours. Even interstellar matter reflects this separation. The average density of interstellar space near the Sun is about 1 atom per cubic centimetre. That is far emptier than the best vacuums produced on Earth. This thin medium fills the space between star systems, but it does not significantly bridge them. Gas and dust drift slowly, influenced by magnetic fields and shock waves, but they do not erase the separations. Cosmic rays and radiation do travel between systems, but even these are diluted by distance. By the time high-energy particles reach another system, they are scattered, deflected, and mixed with contributions from countless other sources. No single neighbouring system dominates the interstellar environment. When considering the physical separation between star systems, it becomes clear that size is not just about objects. It is about spacing. Alpha Centauri feels large in part because it is not embedded in a crowded environment. It stands apart, separated by a gulf of empty space that resists compression into familiar terms. This separation also explains why interstellar travel is so challenging. Even the nearest star system lies far beyond the reach of chemical rockets within a human lifetime. The distances involved are not obstacles that can be bypassed by clever routes. They are fundamental features of how matter is distributed in the galaxy. Scaling models make this clearer. If the Sun were reduced to the size of a grain of sand, Earth would orbit a few centimetres away. Alpha Centauri would be kilometres distant. That gap represents the typical separation between star systems. Even when everything is shrunk dramatically, the emptiness remains dominant. The physical separation between star systems is therefore not an accident or a flaw in the universe's design. It is a natural consequence of gravity, motion, and the way matter cools and fragments. Systems form where gravity wins locally, but motion prevents global collapse. The result is a galaxy filled with islands of matter drifting through a sea of near vacuum. Understanding this separation reshapes how Alpha Centauri's size is perceived. The system itself may span thousands of astronomical units, but it is still tiny compared to the distances that separate it from other systems. Alpha Centauri is a compact structure embedded in a much larger pattern of spacing that defines the Milky Way. As this broader context settles in, another question emerges naturally. If the space between systems is so empty, what exactly fills it? What is the physical nature of the medium that lies between stars, and how does it influence motion, radiation, and long-term evolution? Between star systems lies a region that resists almost every intuition shaped by life on Earth. It is called interstellar space, but that phrase can be misleading if it conjures an image of nothingness in the everyday sense. Interstellar space is not empty in the way a room can be emptied of furniture, nor even in the way a laboratory vacuum chamber can be pumped down. It is a physical environment with measurable properties, governed by the same laws of physics as everything else, yet defined by extremes of low density, weak interaction, and vast scale. To understand how big Alpha Centauri really is, it is not enough to look at the stars themselves or the distances between systems. One must also understand the nature of what fills the space between them. Density is the starting point. On Earth, density is something we experience constantly. Air has a density of about 1.2 kilograms per cubic meter. Water is roughly 1,000 kilograms per cubic meter. Even what we casually call empty space around us is filled with trillions upon trillions of molecules. Interstellar space operates on a radically different level. In the region of the Milky Way near the Sun and Alpha Centauri, the average density of matter is roughly 1 atom per cubic centimetre. Sometimes it is less. In particularly sparse regions, it can drop to 1 atom per 10 cubic centimetres or lower. That number is difficult to grasp without comparison. A cubic centimetre of air at sea level contains about 25 billion molecules. Interstellar space contains, on average, 1. Not 1 billion, not 1 million. 1. And that single atom is usually hydrogen, the simplest and most abundant element in the universe. Occasionally helium atoms appear, and in much smaller quantities trace amounts of heavier elements. Dust grains exist too, but they are exceedingly rare, separated by enormous distances. This low density is why interstellar space behaves almost like a vacuum, but not quite. A perfect vacuum, in the strict physical sense, would contain no particles at all. Such a vacuum does not exist naturally, and is extremely difficult to approximate even in laboratories. Interstellar space comes closer to a true vacuum than anything humans can create on Earth, yet it is still not empty. The presence of even a few particles per cubic centimetre is enough to give interstellar space physical properties that matter over long distances and long times. One of the most important consequences of a low density is the rarity of collisions. On Earth, particles collide constantly. In a gas, molecules bounce off each other millions of times per second. In interstellar space, a particle can travel for kilometres, thousands of kilometres, or even farther without encountering another particle. This changes how energy is transferred, how heat behaves, and how matter evolves. Processes that happen quickly on Earth can take millions of years in interstellar space simply because interactions are so infrequent. Despite this, interstellar space is not static. It is threaded with motion, radiation, and fields. Gas drifts slowly under the influence of gravity. Shock waves from supernova explosions propagate through it, compressing and heating regions of gas. Magnetic fields weave through the galaxy, guiding charged particles along invisible paths. Cosmic rays, high-energy particles accelerated by extreme events, pass through interstellar space, interacting occasionally with atoms and magnetic fields. Temperature in interstellar space is another concept that challenges intuition. Temperature is a measure of the average kinetic energy of particles. In dense environments, temperature correlates with how hot something feels. In interstellar space, where particles are rare, temperature becomes less intuitive. The average temperature of the diffuse interstellar medium near the Sun is on the order of a few thousand degrees Kelvin. That sounds extremely hot, yet it would not feel hot in any conventional sense, because there are so few particles to transfer energy. If a human could somehow be placed in interstellar space without other complications, they would not be burned by heat. They would lose heat rapidly through radiation and freeze instead. The few particles present would not collide with the body often enough to deliver significant energy. This illustrates how temperature and density must be considered together. High temperature does not imply high energy transfer when density is low. Vacuum, as experienced in space, also has implications for motion. In everyday life, motion is resisted by friction and drag. Air slows moving objects. Water resists motion strongly. In interstellar space, drag is essentially non-existent. Once an object is moving, it will continue moving at the same velocity unless acted upon by a force. This is not a special property of space. It is a direct consequence of Newton's first law combined with extremely low density. This absence of drag is one reason star systems like Alpha Centauri can move through the galaxy for billions of years without losing significant energy. Their motion is governed almost entirely by gravity, not by resistance from the medium they travel through. The interstellar medium is too thin to slow them down in any meaningful way. The emptiness of interstellar space also shapes how light travels. Photons can move through vast distances without being absorbed or scattered. This is why we can see stars across thousands or even millions of light years. If interstellar space were dense, light would be blocked or diffused long before reaching us. The fact that the night sky is transparent is direct evidence of how empty space really is. However, transparency is not absolute. Over very long distances, even low densities matter. Dust grains, though rare, can absorb and scatter light, especially at shorter wavelengths. This leads to interstellar extinction, the dimming and reddening of starlight as it passes through space. The effect is small over distances like that to Alpha Centauri, but it becomes significant across larger regions of the galaxy. The presence of interstellar gas and dust also means that space is not chemically inert. Atoms and molecules can interact, albeit slowly. In denser regions, such as molecular clouds, these interactions become frequent enough to allow complex molecules to form. These clouds are the birthplaces of stars. They represent the opposite extreme from the emptiness of typical interstellar space, yet they are part of the same continuum. Between Alpha Centauri and the Solar System, the interstellar medium is relatively uniform and sparse. There are no dense clouds, no strong shock fronts, no extreme radiation fields. This calm environment contributes to the long-term stability of both systems. It also means that the space separating them remains largely unchanged over millions of years. From a physical standpoint, emptiness does not mean insignificance. Even a few particles per cubic centimetre can influence processes when distances are measured in light years. Over time, gas can accumulate, magnetic fields can channel motion, radiation can ionize atoms. The interstellar medium acts as a slow, subtle participant in galactic evolution, rather than a passive backdrop. One way to appreciate this is to consider timescale. In dense environments, change is fast. In interstellar space, change is slow. A chemical reaction that happens in a fraction of a second on Earth might take thousands of years in space. A pressure wave that crosses a room in milliseconds might take centuries to traverse a light year. Physics still applies, but the pace shifts dramatically. This shift in timescale affects how systems interact. Alpha Centauri and the Solar System are separated by a region of space that changes very slowly. Any influence they exert on each other through the interstellar medium is negligible on human timescales. Gravity dominates their relationship, and even that is weak compared to internal forces within each system. The concept of vacuum also extends into modern physics in deeper ways. Even in the absence of particles, space is not truly empty. Quantum field theory describes vacuum fluctuations, temporary changes in energy that occur even in empty space. These effects are real and measurable under certain conditions, though they do not play a significant role in the large-scale structure of interstellar space. Still, they serve as a reminder that emptiness in physics is always relative. Radiation fills interstellar space as well. The cosmic microwave background, a relic from the early universe, permeates all of space with a nearly uniform temperature of about 2.7 Kelvin. This radiation is faint, but it is everywhere. Starlight, infrared emission from dust, and radio waves from various sources add to this background. Space is quiet, but not silent. Interstellar space also contains magnetic fields, typically on the order of a few microgauss. These fields are weak compared to those near stars or planets, but they influence the motion of charged particles over long distances. They shape the flow of cosmic rays and help structure gas clouds. Their presence further complicates the idea of emptiness. Even where matter is scarce, fields persist. When considering the separation between star systems, the nature of interstellar space becomes inseparable from the idea of distance. The vastness between systems is not just a matter of how far apart they are, but how little fills the space between them. Alpha Centauri feels far away not only because of its distance in light years, but because there is almost nothing along the path connecting us to it. This emptiness is what allows light to carry information cleanly across space. It is what allows star systems to remain isolated. It is what makes interstellar travel difficult, not because of obstacles, but because of the absence of intermediate waypoints. There is no gradual transition from one system to another. There is a sharp drop from the gravitational dominance of one star to the near featureless background of interstellar space, followed by a gradual rise into the influence of another system. In scaled models, this is often the most surprising feature. When distances are compressed to something manageable, stars become grains of sand separated by kilometers of empty road. The emptiness dominates the model. The objects themselves feel almost incidental. This accurately reflects reality. Most of the universe's volume is empty space, not matter. Yet that emptiness is what allows structure to exist. If matter were packed more densely, gravity would collapse it into fewer, larger clumps. If it were more diffuse, stars might not form at all. The balance between density and emptiness is what allows galaxies to persist in their current form. Interstellar space is not a mistake or a leftover. It is a necessary component of cosmic structure. Understanding interstellar space reframes how Alpha Centauri's size is perceived. The system occupies a small region of space filled with mass, energy, and motion. Surrounding it is an enormous volume of near vacuum that isolates it from other systems. The contrast between the dense interior of a star system and the sparse interstellar medium is extreme, yet smooth in physical terms. It becomes easier to see why scale in astronomy is so difficult to internalize. Objects are small compared to the distances between them. Interactions are rare. Changes slow. Physics operates consistently, but far outside the range of everyday experience. Patterns only become visible once enough detail is gathered, and Alpha Centauri is one of the rare cases where proximity allows physics to move beyond statistics and into direct structure. When we look at Alpha Centauri, we are not just learning about a single nearby system. We are learning about the nature of stellar neighborhoods themselves, how stars group, how they move, how they remain bound or drift apart, and how local environments differ from one region of the galaxy to another. Alpha Centauri acts less like an isolated example and more like a readable sentence in a much larger text written by gravity, motion, and time. A stellar neighborhood is not defined by sharp borders. There is no fence or edge that separates one star's territory from another's. Instead, neighborhoods emerge from relative distances, shared motion, and long-term gravitational relationships. In the region of the Milky Way where the Sun resides, stars tend to move in loosely associated streams, sharing similar orbital paths around the galactic center. Alpha Centauri is part of this same general flow. Its velocity through space is similar to that of the Sun, which is one reason it remains nearby over long timescales. This shared motion is not accidental. Stars that form in roughly the same region of the galaxy often inherit similar velocities from the molecular clouds that gave rise to them. Over time, these stars drift apart, but some remain relatively close for hundreds of millions or even billions of years. Alpha Centauri and the Sun may not have formed together, but their similar galactic orbits have kept them neighbours for a significant fraction of the galaxy's lifetime. From a physics perspective, this tells us that stellar neighbourhoods are dynamic but not chaotic. Stars do not wander randomly in all directions. Their motion is constrained by the galaxy's gravitational potential. They follow curved paths, oscillating slightly above and below the galactic plane while circling the centre. Within this structure, local groupings emerge and dissolve slowly. Alpha Centauri illustrates that nearby in astronomy is a temporary condition. Right now it is our closest stellar neighbour. In the distant past, another star may have held that title. In the distant future, a different one will. The neighbourhood changes as stars move along their orbits. This motion is predictable in principle, governed by gravity, but complex in detail due to interactions with spiral arms, molecular clouds, and the galaxy's overall mass distribution. Despite this motion, the local stellar density remains low. Even in our immediate neighbourhood, stars are separated by several light-years on average. Alpha Centauri's closeness does not indicate a crowded region. It indicates a statistical fluctuation within a sparse environment. This reinforces the idea that most stellar neighbourhoods are empty by human standards, even when they contain dozens or hundreds of stars within a few tens of light-years. Another insight Alpha Centauri provides concerns the prevalence of multiple star systems. For a long time, the solar system was treated as a typical example, a single star with planets orbiting quietly around it. Closer study of nearby stars, including Alpha Centauri, has shown that this is not the dominant arrangement. A large fraction of stars in the Milky Way are part of binary or multiple systems. In some estimates, more than half of all Sun-like stars have at least one stellar companion. Alpha Centauri demonstrates that multiple star systems can exist in relative isolation without being part of dense clusters. Its binary core is stable, long-lived, and unperturbed by nearby stars. This tells us that stellar multiplicity does not require crowding. It can arise naturally from star formation processes and persist in sparse neighbourhoods. This has important implications for how neighbourhoods evolve. A region filled with binary and multiple systems behaves differently from one dominated by single stars. Gravitational interactions are more complex. Energy can be exchanged internally within systems rather than between systems. This internal complexity allows neighbourhoods to remain relatively calm externally while hosting intricate dynamics on smaller scales. Alpha Centauri also reveals something about mass distribution in stellar neighbourhoods. The local region of the Milky Way is dominated by low-mass stars. Red dwarfs like Proxima Centauri are far more common than Sun-like stars. Alpha Centauri's inclusion of a red dwarf companion reflects this broader trend. While Alpha Centauri A and B attract attention because they resemble the Sun, Proxima represents the majority population. This imbalance matters because low-mass stars contribute less light but persist for far longer. Over time, stellar neighbourhoods become increasingly dominated by long-lived, low-luminosity stars. Alpha Centauri shows this transition in miniature. Its most massive members will evolve and change significantly over billions of years, while Proxima will remain relatively unchanged. Stellar neighbourhoods are also shaped by the interstellar medium they move through. Alpha Centauri and the Sun currently reside in a region known as the local bubble, a cavity of hot, low-density gas likely created by ancient supernova explosions. This environment reduces drag, alters radiation fields, and influences how cosmic rays propagate. The fact that both systems share this environment means their interaction with interstellar space is similar. This shared environment further stabilizes the neighborhood. In denser regions, gas clouds can perturb stellar motion. Shock fronts can compress or erode planetary systems. In the local bubble, conditions are relatively gentle. Alpha Centauri's longevity as a nearby neighbor is partly due to this calm setting. Another lesson from Alpha Centauri concerns scale hierarchy. Stellar neighborhoods sit between two extremes. On smaller scales, individual star systems dominate. On larger scales, the galaxy dominates. Neighborhoods exist in between, shaped by both local and global forces. Alpha Centauri helps anchor this intermediate scale. It is close enough to feel local, yet clearly separate and self-contained. This hierarchy affects how astronomers model the galaxy. Rather than treating stars as isolated points or as a smooth distribution, physicists recognize that stars cluster loosely into associations, streams, and neighborhoods. Alpha Centauri belongs to such a structure, even if that structure is diffuse and temporary. The system also highlights how gravitational influence fades with distance. Alpha Centauri's gravity does not significantly affect the solar system's planets. Likewise, the Sun's gravity does not influence Alpha Centauri's internal dynamics. The boundary between systems is defined by this fading influence, not by physical barriers. Stellar neighbourhoods are collections of systems that are close enough to be noticed but far enough to remain independent. From an observational standpoint, Alpha Centauri serves as a calibration point. Its well-known distance, motion, and composition help astronomers understand nearby stars as a population. By comparing other stars to Alpha Centauri, physicists can identify which properties are typical and which are unusual. This comparative approach is essential for mapping stellar neighbourhoods accurately. Alpha Centauri also reveals something about chemical similarity. Its stars have compositions broadly similar to the Sun's, suggesting formation from material enriched by earlier generations of stars. This chemical kinship is common in local neighbourhoods, where stars form from the same interstellar medium over extended periods. Differences exist, but they are modest compared to variations seen across the entire galaxy. This chemical consistency has implications for planet formation. If the building blocks are similar, then the processes that form planets may also be similar. Alpha Centauri's neighbourhood is not chemically exotic. It is representative of the galactic disk. This reinforces the idea that the solar system is not an outlier, but one example among many formed under comparable conditions. Stellar neighbourhoods are also shaped by time. Over billions of years, stars migrate radially within the galaxy. They move inward and outward from the galactic centre due to interactions with spiral arms and other structures. Alpha Centauri's current proximity does not guarantee it always occupied this region. It may have formed closer to or farther from the galactic centre before settling into its present orbit. This migration blurs the concept of a permanent neighbourhood. What we observe is a snapshot. Alpha Centauri's role as our nearest neighbour is temporary in cosmic terms. This does not diminish its importance, but it places it within a constantly evolving framework. One of the most important lessons Alpha Centauri offers is that scale is relative even within neighbourhoods. 4 light-years is close enough to study in detail, yet far enough to remain unreachable with current technology. The neighbourhood feels intimate on galactic scales and vast on human scales. Physics accommodates both views without contradiction. Alpha Centauri also highlights the absence of central coordination in stellar neighbourhoods. There is no organising force grouping nearby stars together intentionally. Neighbourhoods emerge from shared motion and chance alignment within the galaxy's gravitational field. This lack of central structure is why neighbourhoods dissolve and reform over time. The calmness of the Alpha Centauri neighbourhood also underscores a broader truth. Most of the galaxy is quiet. Catastrophic events like supernovae are rare in time and space. Most stars spend their lives moving gently through sparse environments. Alpha Centauri exemplifies this calm persistence. Its stars shine steadily, orbit predictably, and drift through space without drama. By studying Alpha Centauri, physicists gain insight into what is typical rather than exceptional. The system does not sit at an extreme of mass, luminosity, or environment. It sits near the middle of many distributions. This makes it a valuable reference point for understanding how stellar neighbourhoods generally behave. After spending so much time thinking in terms of mass, distance, energy, and motion, it becomes necessary to slow down again and let those ideas reconnect with something familiar. Physics is powerful because it strips the universe down to quantities that can be measured and compared, but human understanding does not live in equations alone. It lives in scale, in reference, in the ability to place one thing beside another and feel the relationship between them. Returning to human scale does not mean abandoning physics. It means allowing what physics has revealed to settle into proportions the mind can hold without distortion. Human scale begins with the body. A person occupies less than 2 meters of space. A room might span a few meters more. A city stretches across kilometers. Even at this level, intuition already begins to thin. Few people truly feel what 100 kilometers means, let alone thousands. Physics does not expect intuition to keep up. It simply asks for consistency. When we talk about Alpha Centauri being more than 4 light years away, physics is not asking us to imagine the distance directly. It is asking us to understand what that distance implies in relation to everything else we know. One way to reconnect is through time, because time is something humans experience constantly. A second passes without notice. A minute can feel short or long depending on context. An hour has weight. A year carries memory. When physics tells us that light takes a little over 4 years to travel from Alpha Centauri to Earth, it is offering a bridge. That light began its journey before certain moments in your life occurred. It has been travelling, uninterrupted, through interstellar space while seasons changed, while days accumulated into years, while countless small events unfolded on Earth. This does not make Alpha Centauri feel closer in a practical sense, but it makes the distance relatable. 4 years is not abstract. It is lived time. It is enough time for a child to grow noticeably, for habits to form, for routines to change. The distance becomes something that unfolds rather than something that simply exists. Another way back to human scale is motion. Humans move slowly. Walking speed is about 1.5 meters per second. Driving on a highway might reach 30 meters per second. Even the fastest aircraft remain well below the speed of sound. When these speeds are compared to the speed of light, the gap is extreme. Light moves nearly 300,000 kilometers every second. No amount of everyday motion prepares intuition for that. Yet physics does not ask us to match that speed. It asks us to accept the consequence. Even if humanity built machines capable of traveling faster than anything we know today, Alpha Centauri would still be far. The distance is not an obstacle caused by technology. It is a feature of space itself. Returning to human scale also involves recognizing limits. Humans evolved to operate within a narrow band of distances, forces, and timescales. Physics operates across all of them. The mismatch is not a failure of understanding. It is a reminder of perspective. Alpha Centauri is not meant to feel close. It is meant to demonstrate how sparse and extended the universe truly is. Scale models help here, not as metaphors, but as proportional translations. If the Sun were reduced to the size of a small coin, Earth would orbit a few meters away. The solar system would fit inside a modest field. Alpha Centauri would not be nearby. It would be kilometers away. The emptiness between systems would dominate the model. This does not exaggerate distance, it preserves it. What tends to surprise people most is not how far Alpha Centauri is, but how little fills the space between. Human environments are dense. Walls, air, sound, objects, movement, all crowd perception. Interstellar space removes almost all of that. When physics describes 1 atom per cubic centimeter, it is not trying to sound dramatic. It is stating a condition. Most of the universe's volume contains almost nothing. Returning to human scale means accepting that emptiness as real, not as absence, but as structure. Emptiness is what allows stars to exist without constantly interfering with one another. It is what allows light to travel cleanly. It is what allows systems like Alpha Centauri to persist undisturbed for billions of years. The universe is not empty despite its structure. It is structured because of its emptiness. There is also a psychological adjustment that comes with scale. When humans hear about vast distances, the instinct is often to feel small or insignificant. Physics does not imply insignificance. It implies context. Alpha Centauri does not diminish the solar system by existing, it places it. The solar system is not less meaningful because it occupies a small region of space. It is meaningful because it is a region where complex structures, chemistry, and life emerged. Physics does not rank importance by size. An electron and a galaxy are both essential to the universe's behavior. Alpha Centauri's scale does not make Earth trivial. It makes Earth specific. Another part of returning to human scale is understanding that comprehension does not require visualization. It is not necessary to picture 4 light years of space. It is enough to know what that distance does. It delays signals, it separates systems, it limits interaction. Physics allows understanding through consequences rather than imagery. The same applies to mass and energy. The fact that Alpha Centauri A produces more energy than the Sun does not need to be imagined as brightness or heat. It needs to be understood as output, as power, as influence. The fact that Proxima produces very little energy does not make it unimportant. It places it in a different physical regime. When these ideas are allowed to settle, something subtle happens. The universe stops feeling exaggerated. It stops feeling like a collection of extremes piled on top of one another. Instead, it begins to feel orderly. Large things are large because conditions allow them to be. Empty space exists because motion and gravity balance in specific ways. Alpha Centauri is not impressive because it is close or far. It is impressive because it fits exactly where physics says it should. Returning to human scale also means letting go of the need for completion. Physics does not end with Alpha Centauri. It does not end with the nearest stars or the local neighbourhood. Those are simply the regions where measurement is easiest. The same principles apply everywhere. Alpha Centauri is a nearby example, not a boundary. There is a calmness in that realization. The universe does not behave differently beyond our reach. It behaves consistently. Distance does not introduce mystery so much as delay. Scale does not introduce chaos so much as patience. At a human level, this allows curiosity without urgency. There is no need to resolve the universe. There is no need to reach Alpha Centauri for it to matter. Its existence already informs understanding. Its distance already teaches scale. Its structure already reflects universal laws. When attention returns to the immediate environment, nothing has changed physically. The room is the same, the night's the same, but perspective has shifted slightly. The awareness that beyond Earth's atmosphere lies a region of near vacuum stretching for trillions of kilometers, followed by another system of stars bound together by gravity, changes how closeness is perceived. Human scale becomes something chosen rather than imposed. You can think in meters or in light years, in seconds or in centuries. Physics allows both. It does not demand that the mind stay at one scale. It only asks that scales not be confused. Alpha Centauri in this sense becomes less of a destination and more of a reference. It marks the distance at which the solar system stops being alone and begins to be part of something larger. It marks the transition from planetary thinking to stellar thinking. Beyond it lie countless other systems, each separated by similar expanses of space, each governed by the same quiet rules. Returning to human scale does not collapse those distances. It integrates them. It allows the knowledge of scale to exist without overwhelming attention. The universe remains large. Space remains empty. Time remains long. None of that presses inward unless invited. Physics offers one final reassurance here. Nothing about Alpha Centauri's size, distance, or structure makes human experience fragile. The vastness of space does not threaten proximity. It preserves it. The separation between systems means that local environments remain stable for long periods. Earth is not constantly disturbed by nearby stars. The solar system is not crowded. Stability is a consequence of scale, not a victim of it. With that understanding, the journey outward through physics does not end in alienation. It ends in grounding. The universe is large, but it is not hostile by default. It is spacious, structured, and patient. Alpha Centauri exists quietly within it, doing nothing dramatic, following the same physical rules that govern everything else. And with that, attention can rest again on the present moment, carrying with it the knowledge that beyond this small human scale lies a much larger one, not pressing in, not demanding attention, but simply existing, vast and orderly, exactly as physics describes it.